Okay, good evening, everyone. So, welcome to week six, assignment six session of the Introduction to Semiconductor Fundamentals course offered by NPTEL. And I'm Shahzan Bhatt, and I'm a direct PhD student at Electrical Engineering Department at IIT Bombay. And let me just so I can see people have joined. So let me just start directly what we have already covered. So it's just my ritual to recap everything what we had done till now so that you can have a framework in your mind where we started from and where we are going to end. It should be absolutely clear in your mind that what is the map of this semiconductor fundamentals course, because once you have this map in your mind, you are going to understand some I should say complicated concepts easily once this is absolutely clear in your mind. So can any one of you just acknowledge once whether the everything is absolutely clear, audio, video, as well as the presentation slides? Can anyone confirm just quickly? Is my am I audible, and is my video clear, and are the slides visible?
Audible, sir. Clear, sir.
Okay, fine. Thank you. Okay, so let's get started then directly. So let's directly jump into what we had covered and just spend maybe 10-15 minutes on that. So you guys now know we started with single atoms. We considered its potentials, and we computed how the potential looks like, something kq by r, something like that, which is the potential felt by the electron in the vicinity of this positive charge. Then you considered many number of those atomic nuclei or atoms inside the solid, and you considered them to be a repetitive arrangement of the atoms, something called as periodic arrangement. And once you do that, you use something called as Bloch's theorem plus chronic penny to arrive at, this is the chronic penny model, to arrive at something called as band structure, where you show that there are certain values of the energies of electron which are acceptable, and you show them in something called as first Brillouin zone. This is something called as reduced zone representation, and you showed that it looks something like this, where these are the allowed or acceptable energy levels in the first Brillouin zone of the crystal. And that we have already covered, where the minima of this is called as conduction band and the maxima of this is called as valence band. This is the conduction band and this is valence band respectively. And then you showed that how we can move on to understand the conduction picture, conduction of electrons, where you show that you can have electrons here which can be fully occupied, but if one of the electron goes here, a vacancy is created, this electron moves here, then the other electrons move here, and you have a conduction picture once the, let's say, the electric field is applied in this direction, and the electrons start to flow in these bands. And then you show that if you have a single chunk of a semiconductor, let's say silicon semiconductor, you have intrinsic carriers, you have electrons, you have holes, and under equilibrium conditions, and the product is equivalent to Ni square. This is just a single chunk of semiconductor. Now, you show that what happens whenever you apply the electric field, you have something like this bending where you have the electron and the hole in this electron and hole pairs are generated. Okay, so you also know that now this electric field is equivalent to the gradient of the energy level, spatial gradient of the energy level. And that's why you have the band bending near the if you apply the potential to a semiconductor chunk. Now, when you combine the two semiconductors, you got something called as PN junction. And before that, here you were taught about electrostatics, where you learned about the drift, you learned about the diffusion equations, you learned about the Poisson, you learned about the continuity equation, and where you maybe you ignored the generation and recombination parts, but you learned about the drift component, the diffusion component, and the Poisson equation. And you then shifted towards understanding what happens when you combine the two semiconductors. You form something called as depletion region here, where there is a bending like this in an equilibrium, and you have a common Fermi level for it. Okay, so this region is the depletion region where you have the positive ions, immobile ions on this side and negative ions on this side. And you can modulate this depletion width, and it depends upon the doping, the concentrations, as well as the inbuilt field. So it depends upon VBI plus minus V applied. So if you apply the voltage, you can modulate this barrier accordingly. Then you shifted on to understand the forward bias case, the reverse bias case of the diode, and you showed that under forward bias it looks something like this, where you have reduced the barrier and you have now two different Fermi levels. One is like here, another is here, and in between the Fermi level looks something like this. And you have this conduction band, you have this Fermi level, and what you showed that is you have the electrons present here as a distribution n of E, which is a product of Fermi function times the density of the state. And those electrons which are present in this Fermi tail are able to diffuse to the other side. That's why most of the current flows because of the diffusion in case of the diode. And similarly, you have the hole distribution. Those holes which have energy about this, they are able to diffuse to the other side, and you have a conduction because you have applied positive on this side, negative on this side, because this is a forward biased case. And what you then showed is that if you consider the reverse bias case, you have something like huge barrier present between, where this is the Fermi level of this is the Fermi level of P side, and in between the Fermi level looks something like this. And this is the depletion region, and depletion region width increases appreciably under the reverse bias. Here, the depletion region width decreases under the forward bias. So this is what you have covered till now, and uh, what we also did is that we understood how we can plot the different concentrations. If you have, let's say, this is P side, this is N side, this region marks the metallurgical junction, and let's say you have charges like positive ions here, negative ions here. This is the depletion region. This is the depletion region. Okay, so you have Q times ND here, you have Q times NA here. These are the immobile charges. Then you showed that how you can actually draw the electric field profile. If you know this rho as a function of x, which is space charge, this is space charge in the depletion region, you can integrate the space charge to get the electric field by using something called as Poisson. So this is from x1 to x2, and you got the electric field. If this is equally doped on other side, if there is equal doping on both of the sides, then you get a electric field profile something like this by integrating the space charge. Okay, so this is electric field as a function of x. So this is x. Okay, you get electric field profile something like this, where there is a maximum electric field in the center, because at the center, most of the electric field lines will be passing through it. If you just consider a imaginary plane here, then all of the electric field lines will be passing through that plane. There'll be huge flux in the middle. So that's why there is a peak in the middle of this space charge region for the electric field. Then you can go on integrating this particular electric field. You know, if you can obtain the potential as a function of x equals to minus integral of electric field times dx from x1 to x2, then you can get the electric field profile, so the potential profile as a function of x. And if you invert this potential, you can get energy, potential energy. Potential energy as a function of x is equivalent to some minus q times v of x. So you have to minus it and you have to multiply it with the electronic charge, you get something like this. That's where the band bending actually comes from. So it's all coming from the simple electrostatic picture. So that's what you have already covered. And this is the key aspect you should be keeping in mind, where actually the flow goes from, and what you have to do from the beginning, because this is applicable in almost all of these devices if you just know how to compute everything. And later on, when you will go in higher courses, this is going to be absolutely important in doing the simulations of these devices. Even the industries rely on these particular aspects in understanding how the band diagram or bands will bend in presence of different charges inside the semiconductor. So there, the basics are going to be just these particular electrostatic concepts. And this is what you have already learned. Now, what happens if you know this energy? You can compute concentrations, and P you can compute other these of electron concentrations. You can compute hole concentrations. Okay, so that's a different picture, and you can basically solve something called as Poisson equation again in order to compute the potential variation. Let's say you have Q times P minus N plus ND minus NA divided by epsilon. This is the Poisson equation you can solve in order to compute the overall potential profile of a device. And this is heavily used, heavily solved in a tool, something called as TCAD. TCAD is an industrial tool. It's used to compute the band diagrams of the different electrical devices. Let's say you have a PN junction diode, you have BJTs, you have maybe MOS capacitors, MOSFETs, you have Schottky diodes. If you can do this kind of a simulation, you are just ready to go in the any of the industries, top industries. Let's say Micron or maybe IBM. They all use these kind of tools, particularly the TCAD and other transistor CAD tools. So you just have to understand the basics of this. So that's the overview of it. And now where we are heading towards today is that now you have understood what happens when we conduct two semiconductors. You have P, you have N. Now you have to understand one more thing is that when we apply the voltage to this particular device, let's say positive, negative, this is we applied, and let's say here you have the space charge, okay, with certain space depletion width. You know that whenever we connect these leads, these are called leads or probes, whatever you call them. They are used to probe the currents and the voltage. Whenever you do such thing, or you apply certain some voltage with the help of leads or probes, you have to connect them here to a certain region. Okay, and these wires, they are metallic. Okay, so they are not semiconducting anymore. So you are connecting a metal here to a semiconductor. So that's what our next problem is. We want to understand what happens when you connect a metal to a semiconductor. So this is our next topic is going to be. Why this is important? Because at the end of the day, you're not just going to play with semiconductors. You are going to use semiconductors in the devices. Let's say you have a device, you are going to use the semiconductor. Let's say this is a microprocessor, microprocessor. Microprocessor has millions and billions of transistors. Let's say it has billions of diodes. Okay, which are used to control maybe switch on and off certain devices inside it. And you know that diode is used to switch things on and off. If you apply forward bias, you have turned it on. You apply the reverse bias, you have turned it off. And by this, you get the control of something called like 1 0 1 0. You got a control of on and on to turning it on and off, and you can convert it into ones and zeros. Okay, that's the binary code. That is how the processors and computers work, the binary language. And now let's say you have a microprocessor here. What is going to happen is that you might have seen all those chips in your maybe lab, which look something like this, maybe 8-pin chip or maybe 14-pin chip. Inside there are transistors. There are maybe diodes or transistors present, but we cannot see inside because it's almost covered with a black plastic type of packaging. So that's called as electronic packaging. But all you can see are those golden pins which come outside. But internally you cannot see. But they are connected internally with these diodes, which are kind of microfabricated. They are a very micron level or nanometer level devices present there. But you can see those gold pins outside. But they gold, that is a metal basically. And when the metal comes in contact with the diode, that's where the problem comes now. That's what we want to understand. Now you have a metal, it has come into contact with a semiconductor, and you want to understand what is going to happen at this junction, which is going to form because of the metal and semiconductor. Because it's now no longer a same material which has come together. It's we are not probing or we are not using semiconductor pins or something like that. We are probing with the metallic pins. Okay. So now you want to understand it, and we are going to dive into this particular scenario. What is going to happen when you connect the metal to a semiconductor? Okay, so that will be our topic of concern today, something called as metal semiconductor semiconductor junctions. Okay, so this is going to be our topic of concern today, and all of the problems are based on metal semiconductor junctions, and few of the problems are based on MOS that will be looking in this today's session. Now, what happens is exactly right here. Now, first of all, what is if you have a let's say a semiconductor here. Let's consider for timing it's n-type semiconductor. Okay, we hardly use an intrinsic semiconductor for these purposes because the conduction is usually very low. So you have to dope it to make it n-type so that the Fermi level gets near close to the conduction band, and you can have conduction pretty much easily in case of doped semiconductors, and you have more number of carriers obviously present because here now you can see that Fermi level is close to the conduction band of the semiconductor. That's why there are many number of electrons present in the system now. Now, this is the band diagram corresponding to this particular semiconductor. Now let's bring in a metal. Okay, let me just take it. Let me just draw it here. And when we have the metal, let's consider this as a metal. Metal is a conductor. It's a pure conductor. What you have been studying from the class 12th or class 11th electrostatics. So all of the rules you have studied about the electrostatics, they apply to the conductor, and a little bit of modifications you have to do, and then you can apply in the semiconductors because semiconductor is not a pure conductor as such. There's a band gap. In case of metals, there is no band gap. Now, how you draw the band diagram of a metal band diagram, particularly of for a metallic system, you just draw a single level, which is the maybe you can call it conduction band or you can call it Fermi level of a metal. It depends upon you. Some people use it as a conduction band. It doesn't really matter, but you can call it Fermi level of a metal. Why it's the Fermi level of a metal? It's because it's just that there are so many energy. The energy levels are something like this in a metal, where this particular Fermi level is exactly inside the conduction band. Okay, there if somebody may ask you that is there a band gap in a metal? Yes, there is, but some of the band gaps are pretty much very higher in energy. When you see the ek of any metal, if you see a ek of any metal, let's say this is a metal, let's say this is a metal x, any metal, it so happens that the Fermi level lies around this particular thing. Okay, this particular thing, but there are bands above also, and they go on and on in kind of in increasing energy fashion. But what happens mainly is that all of the levels up to this particular point are filled in a metal. Okay, so they're completely filled up to the Fermi level because the Fermi level is lying inside the band itself. This is the band of the metal, the energy band, and the Fermi level is lying inside it, and all of the levels up to the Fermi level are completely filled in metal. And if somehow it happens that you can traverse this particular band in a metal, you have to spend this particular gap. There are certain gaps in a metal. If you just see the dispersion diagram of any metal, you take a gold, you take silver, you take any of the metal, because at the end of the day, metal is a crystal. Okay, and you saw that uh, whenever you have a crystal, you have a periodic structure, you get some acceptable and not unacceptable values. But for the metals, because of the Fermi level being directly in the conduction band itself, most of the conduction takes place because of the electrons present here, just few kTs above and below the Fermi level. So that's why we never talk about the band gap in a metal. Okay. Otherwise, if you just go to a very higher energies, and you might see that certain values of the electrons are not acceptable. That means there is a band gap. Just you can just randomly search dispersion diagram of maybe nickel. You can see that there are certain gaps in the band structure where the allowed values are, where there are no allowed values for the electrons. Okay, but so what happens is that I showed you here is that the Fermi level up to this particular point is completely filled in a metal. Okay, so this is the Fermi level of a metal. That's why we can sometimes call it conduction band, we can sometimes call it Fermi level, but it's better to call it Fermi level of a metal. And above these states are empty, these states are completely filled. Okay, so that is the band, I should say, the band diagram of a metal. And it's quite kind of, this indicates that there are so many number of electrons present here, because the Fermi level is now kind of it has penetrated into the conduction band, and it's in the conduction band itself. There are huge density of states. So whenever you, let's say, draw the uh, I should say the density of states for any of the metal, you see that there are many of the electrons involved in the conduction. Sometimes s electrons, sometimes d electrons. These s and d are the orbitals of the electrons. And whenever you draw this particular diagram for a metal, let's say you have something like this, you see that the Fermi level, if Fermi level lies around here, this particular thing is Fermi level lies around this point, you can clearly see that this particular, let's say, there are other orbitals present. Let's say this is d orbital. Then what happens is that many of the electrons can get excited to this Fermi level quite easily. And anyways, the number of electrons present up to this level are so huge that it really doesn't make sense to kind of, I should say, there are so many number of electrons present at this particular Fermi level, that this is something called as, that's why these particular electrons are called as nearly free electrons, or you call it free electron gas. Okay, why? Because so many number of electrons of the order of 10 to the power 28 per centimeter cube electrons are present, free electrons are present near the Fermi level. Okay, it is as if that there is electron gas present. Electrons almost act like a gas molecules there. And all of the classical theories for what you apply for the gas, let's say you have a gas molecules present in any container. You know that its average energy is 3 by 2 kT from the Boltzmann statistics. You can apply the same thing here. If okay, so it's very weird, but that is what actually happens. You can apply the same thing here. The electrons present here actually have energy equal to 3 by 2 kT, just like the gas molecules. So that's why it's called as free electron gas. Okay, so metals are very special in terms of what actually they hold. Maybe we are not taught that much about the metals, but they are very special in terms of the conduction and in terms of the properties. So let's not go deeper into this particular fact, but this is just to kind of appreciate what the metals hold for us. So now we have many electrons present here near the Fermi level. Okay, so what is going to happen when we connect these two? Now we don't exactly show these particular regions in a metal. We just show a single Fermi level, and we consider that up to this Fermi level, electrons are totally filled. This is totally filled. The electrons are totally filled up to this level. Huge number of electrons. And when you bring in the semiconducting system, which is having conduction band here, Fermi level here, valence band here, close to this particular thing, you make a contact. And what happens when you make a contact? That's what we are going to see at page. When you just make a contact, now it depends upon few things. It depends upon whether the Fermi level of this particular metal is greater than that of the Fermi level of a semiconductor. Or rather, I should say there is something called as work function. Work function is that if you have Fermi level of a metal, let's say you have a semiconductor, this is its Fermi level of a semiconductor, there is a level called as vacuum level, vacuum energy. It's the energy which you need to give for the electrons to completely isolate them or completely make them free of the metallic structure or any of the semiconducting structure. So this particular this particular thing is called as work function of a metal. Work function of a metal is the energy which you need to give for the electrons to jump to the vacuum level or to come make it totally free, okay, from the force of attraction of the atoms. And this particular thing is called as work function of the semiconductor. It is measured with respect to the Fermi level because that is the highest energy level of the electron. The Fermi level is the highest energy level of electron. Okay, that is what the definition is basically for the Fermi level. All right, so now what happens is that you have the work function difference. This particular case here is work function of metal is greater than work function of a semiconductor. That is what basically here you can see from this figure because you have chosen this particular to be n-type. Now it may so happen that this particular thing may be here, the Fermi level of a metal. Then in that case, phi m may be less than phi s, and we will see what is going to happen in different scenarios. What is going to happen with if a work function for metal is less than some work function of semiconductor and work function of metal is greater than that of semiconductor. So you remember that this work function basically you might recall from something called as photoelectric effect, where you in class 12th you might remember that you studied about photoelectric effect that certain if you give certain energy photons to a metal, you can knock off the electrons. And that particular energy is the actually the work function of the metal. Okay, if you need to knock out the electrons from the metal, you need to give at least this much amount of energy. Photoelectric effect. Okay, that's what the 1905 Nobel Prize was given to Einstein. And this is the same work function in all of the conducting systems, semiconducting and metallic systems, as well as other systems of the in electronics particularly. And now, what are the other levels here? You call this particular thing as electron affinity, the distance between the energy gap, the energy difference between the vacuum level and the conduction band. You call that as electron affinity, and you call this particular thing as something called as ionization potential. If you directly just knock off the electron from the valence band to the vacuum, this is something called as ionization potential. You ionize that particular molecule or atom, because if you have an atom here in a semiconductor, maybe silicon, uh, and it might have some electronic configuration. So it depends upon how many electrons are present in the outer orbital. Okay, and these inner orbitals are basically, I should not say show. Let's say these are s electrons, one s two electrons, and let's say because below here there are those inner orbitals present, one s2, two s2, 2p6, 3s2, and so on and so forth. Okay, so what happens is that most of the time these inner orbitals do not take part in conduction, that they are tightly bound to the atom. It is only the external or outer orbitals which take part in conduction. That is what that particular picture basically showed. If you have the band like this, you have a band like this in EK, and you have bands like this. You have electrons here, but these are inner orbitals, mostly s orbitals, inner s orbitals, 1s2 or 2s2. These are inner orbitals of a silicon, and they don't take part in conduction at all. But it may happen that if you just bring in a photon of very high energy, and if that hits these electron, it can knock out that particular electron, and that particular is called as ionization potential. You can totally ionize it. You can interact with the innermost electrons. That's what this I basically is. But this is not mostly used in our case because it's a very destructive process if you just play with the inner electrons. Mostly high energy physics people, they work with these electrons, but we are not concerned mostly with these electrons. So that's why people don't show these ionization potentials. We're mostly concerned with the work function. We're mostly concerned with the electron affinity. And now you have to interplay. Now you know this particular thing is the band gap of this semiconductor. So this is EC minus EF. You know all these relations from the earlier classes. Now you just have to play with these. And now what happens when you make a contact of this particular junction? You know that Fermi level here on this side, the Fermi level is higher. So the Fermi level is higher than that of this particular thing. Or in other words, the work function of the metal is greater than that of semiconductor. That's what this basically shows. But if you just understand what happens in PN junctions, this is the similar concept. If you had the Fermi level here of N-type higher, the Fermi level of P-type lower, then you knew that because of the difference in the Fermi levels, the electron goes from higher Fermi level to lower Fermi level, just like water dripping from higher potential to the lower potential. You have you have more water here, you have less water here, it will drip to the other side until there is equilibrium. Similar concept, okay, just in terms of different things you learn, in terms of work function, you have to understand it now. But this is the similar concept. You don't need to complicate things. So electron will go from this higher Fermi level to lower Fermi level up to when? Up to the point Fermi level is flat for the system, because now you're combining two different systems. When they were separate systems, they had different Fermi levels because they were separate. Whenever you have a single system, that has to have a single Fermi level. It cannot have two different Fermi levels. Under any circumstances, it can, some circumstances, non-equilibrium circumstances, it can have, but under equilibrium, it cannot have two different Fermi levels. So whenever it does so, the electron goes from this region to this region towards the metallic region. So what happens is that you get a flat Fermi level in equilibrium. This is in equilibrium. Equilibrium. Okay, when you just made the contact, just made contact. This happens as soon as you fabricate it. As soon as you deposit a metallic layer over the semiconductor, this happens abruptly within fraction of seconds. Okay, this is the Fermi level, overall Fermi level now. So what happened is that you brought the electrons from this region to this region. Now the electrostatic potential of this particular thing will go up so that it can align the Fermi level. And because of that, you now have a band like here, this. And why did that happen? Why it went higher? Because you now the electrons came from this region to this particular side. Now, as soon as the electrons will keep on pumping into the metallic side, it will keep on rising the electrostatic potential of that particular side. So on that, then what's going to happen with time is that with time the electrostatic potential energy of this side will rise so much that it will stop further movement of the electrons. Electrostatic potential energy rises means the band goes high. That means now if some other electrons have to come near this particular region, they have to spend more energy. That's what this band bending shows. That's what this band bending shows. Because the electrons went from this region to this region. So now electrostat, this particular energy raised. Now if any electron wants to stay here at this particular site, they have to spend more energy. That's what the rising part shows. This is the potential energy of the electron. Okay, that I've been highlighting many times. This is the potential energy of electron. So this is the electron potential energy, this is the X. So now you have the metallic Fermi level and semiconductor Fermi level aligned. This is the conduction band, this is the valence band, and you have the let me just take it here. You have the vacuum level here. Okay, there is actually a vacuum level like this. There is also a bending in that particular vacuum level because you cannot change the respective electron affinities and other things of a material. They are the material constants. Okay, this particular thing you cannot change electron affinity, the work function of semiconductor, the work function of a metal. Okay, you cannot change these things. So
Sir,
that's why you
want to remember, sir, electron affinity, sir. Please repeat again.
electron
Elect.
affinity just there is you don't need to remember any definition for it. Just the energy you need to spend in order to send the electron from the conduction band to outside to vacuum level. That's the electron affinity. As simple as that. In order to make the let's say those conducting electrons, the electrons present here, they are the conducting electrons. They are not totally free. If you want to totally make them totally free, you just have to spend some energy, which is called as electron affinity. Those electrons will then go to this particular vacuum level and they'll be out of this particular system. Okay,
Okay, sir.
got it. That is the simplest. You don't need to remember any definitions at all. Just you can just understand the concept and apply that concept everywhere. So these are just the energy differences. That's it. There is no need to remember the definitions or what is a work function. If you just understand that what these quantities do and where they come into picture and how you have to use them, that's it. No need to remember any definition. Okay, so it is just the energy difference between the E vacuum and the conduction band of the semiconductor. But this is a material property. You cannot change it. It is governed by the internal crystal, internal material, internal system of a particular semiconductor. That's what it is. You cannot change it. Just like you cannot change the work function, you cannot change the work function of a metal. So that's why this particular bending is in the vacuum level is because all of these quantities have to remain same no matter what happens. Just like if there is a band gap of Eg equals to 1.1 electron volt, that has to be here also. That has to be here also. It has to be 1.1 throughout. You cannot change the band gap of a semiconductor under any circumstance, except if you change the temperature and other things. But this is an equilibrium, so a band gap cannot change by its own. That's why when you draw the band diagram, you show these levels to be same at every point. If you have given a very kind of if you have clearly seen it in all of the band diagrams, this is same at every point. It cannot change because you cannot change the band gap under equilibrium. Okay, now just let me remove it. Let me remove this
Sir,
thing. Yes, you have a question?
sir, we can say that equilibrium affinity, electron affinity in Venn
Mm,
diagram.
yeah, that's what I have shown here, right? Electron affinity is just a material property. It does not matter whether it's in equilibrium, whether it's a non-equilibrium. It is just the amount of energy you need to give to a particular system in order to extract the electrons from the conduction band to the vacuum energy. Okay.
Okay, sir.
And now in other words, in periodic elements, you might remember we used to define electron affinity of certain elements like fluorine, chlorine, bromine. The electron affinity is higher. That means the electron attracting capability is more. You can, if you want to just go dive deeper into that, you can go into that elemental type of chemistry basically in order to understand the electron affinity. But this is how we actually define it in semiconductors. Okay, just a simple concept, energy difference, that's it. Just like the band gap, just like the band gap. Okay,
Okay, sir. Got it.
now okay, so now what happens is that now you have made the contact, you have seen that what happens here is that there is a band bending. Now you see that once this band bending happens, there are now, if, for example, if there is any electron here present, it cannot directly go onto this particular region. Why? Because there is a barrier present here, now here. There is this, oh shoot, there is this particular barrier here. Now, this particular barrier has been given a name. It's called as phi b. It's called as Schottky barrier. Schottky barrier. I think I missed a C. It's called as Schottky barrier. And it creates a, I should say, whenever people try to make contacts in devices, or let's say whenever we connect a metal to a semiconductor, we don't want Schottky barriers to happen. We mostly want ohmic barriers to happen. What is ohmic and what is Schottky? That's what we will be actually talking about. So uh, there is something called as rectifying contact, and there is something called as ohmic contact. In rectifying contact, the current behaves like that of a PN junction. The IV looks something like this. The current only increases after a certain voltage, and if you apply it in reverse mode, there is no current. That is rectifying contact, just like a diode. And ohmic is just like Ohm's law, V equals to IR. Okay, a straight line. It conducts in the forward region, it conducts in the backward region. It's just like a resistor. Okay, V equals to IR is just like a resistor. You have the resistor, you apply current in this direction, you apply voltage. If you have a resistor, you apply voltage like this, it will conduct. If you have a resistor, you apply voltage like this, okay, it will still conduct. Okay, it doesn't matter, it doesn't differentiate. But the thing is, what happens here is that you have made a rectifying contact if you make a contact something like this, because now you have a barrier present here. The electrons are not easily going to flow from the one end to the other end. Now we are going to study what happens when you apply a bias to this. When you apply bias to this, what is going to happen? That is what we will be dealing in the upcoming slides. What is going to happen to this particular system when you are going to apply the bias? Whether it's going to behave as a rectifying contact, whether it's going to behave as a ohmic contact, that's what we are going to see. All right, so this is the particular scenario. Now, this particular scenario is in equilibrium. This is under equilibrium condition. When the contact, when you have just contacted the, or there is the metal and semiconductor are just in contact with each other. Or rather, I should say, this is not under, or I should say, that's my mistake. This is when both are separated. This is semiconductor. This For this case, the contact is not made. For this particular case, this is when the contact is made between a metal and a semiconductor, and this is under equilibrium condition. As soon as you make the contact, the barrier gets formed. Why? That we showed earlier, because of the difference in the Fermi levels. Now you see that this particular barrier here gets formed, and you can compute these particular barriers knowing the vacuum level. Now you know this particular thing. Here is the electron affinity. This particular thing is work function of semiconductor. This particular thing is, okay, let's not draw it. You know that this particular thing is work function of a metal. Let's not draw it. With respect to the Fermi level, this is the Fermi level for metal. And below it, all of the states are completely filled. There are so many number of electrons present here at the Fermi level. Okay. Now you want to find this particular thing, which is something called a Schottky barrier. The barrier height. How much is the height of this potential barrier? This is just like a barrier to the. This is just like you have a you have an electron, and there is a barrier for the electron. There's a wall. Electron cannot. There are only two chances for the electron to go to the other side of the wall. Either it can go above the wall or it can tunnel. That's what actually happens in these devices. There are only two reasons, or there are only two opportunities for this electron, because it's a quantum object, it's a quantum particle, so it can either tunnel or it can go above the wall. This particular is called as thermionic emission, thermionic, and this is called as tunneling. So that is what happens in these Schottky diodes. They both happen. and under what circumstances they happen, that's what we're going to see. And now, how do you compute this particular barrier height? You know that it will be whenever the contact gets formed from this particular scenario, you can see the difference in the Fermi level of the metal and the electron affinity will be the height of this particular barrier. Why? Because this particular thing, this is the, let me just rub it, and let me just, when the electron goes from this higher Fermi level to the lower Fermi level, and in order to this particular thing goes up because now more electrons are present in the metallic system, so that particular difference gets reflected in this particular barrier, and it raises the barrier, this particular barrier, by the amount of the difference between the Fermi level of a metal and the electron affinity of a semiconductor. That is what this particular, it's just a simple geometrical thing, you can show it, but these are all energies, these are not any geometrical quantities, these are energies. And you can show that this particular barrier, basically what gets formed here, this particular barrier height is basically, if you just write barrier in terms of potential, just neglecting the q's, if you multiply it with q, this is the potential energy. If you omit q's, this is just the potential. Okay, phi b is the work function of a metal times the electron affinity of a semiconductor. Okay, this is the electron affinity of a semiconductor, this particular thing. At yeah, this is the electron affinity of a semiconductor. And now what happens is that, what is next? Let me just see this. Hmm. Okay, so do you have any questions up to this point? Maybe I just. So now this is one type of a contact which gets formed. Now what is the other type of contact? Remember here, this was N type. The Fermi level was close to the conduction band. This one. Okay. What happens if you have a P type? The Fermi level is close to the valence band. Okay. So this here you have a P type. The Fermi level is close to the valence band, and now you see that all of a sudden the work function of a semiconductor, shown in pink, shown in red, is greater than that of a metal. Okay, now the work function of a semiconductor becomes greater than that of a metal. And now, because this Fermi level is higher than that of this, you see electrons moving from this region to this region. And because of that, what happens? There is a band bending in the opposite direction. Okay, now these two Fermi levels have to be aligned in the equilibrium condition. So what happens because of that? The band bends in the opposite direction now. And you see that there is a band bending in this particular direction. And now a barrier gets, actually there is a barrier also here. This particular thing, if you see, oh God, this particular thing is also a barrier here. And you see that there is a, in the previous case also, if you saw that there is a bending, just like what happens in the depletion region of a diode, that means there is, this particular region is the depletion region of it. It's the depletion region of this particular PN junction, or not PN junction, a Schottky diode. Because when you make a contact like this, and you make a contact like this, and this is, I call this particular region up to this as a depletion region. Why is this a depletion region? Is because you have depleted depleted this region. Depleted means इलेक्ट्रॉन्स को निकाल दिया है इस पर्टिकुलर रीजन से. You have depleted means कम कर दिया है. So you have taken electrons from this particular region and sent into this particular region. Earlier, that's what I said. The electrons went from this to this. You have, in this region, you have depleted it of electrons. That's why this is called as depletion region. Now, what is left is only the immobile ions. You have depleted this particular region of the electrons. Now, what is left is only immobile ions because this was n-type. N-type is positive and an extra electron. The n-type is positive and an extra electron. When these electrons went to the metallic side, it got depleted of electrons, and only positive ions remain. Positive ions remain, that means there is a depletion region formed. This is the depletion region formed here, just like in a p-n junction. But one difference here is that it's only a one-sided depletion region. There are no negative, I should say, ions on the other side. This particular positive is balanced by the electrons on the metallic side. That is the only difference between in the p-n junction depletion region and here. In p-n junction, you used to have positive here, you used to have negative here. Why? Because this was semiconductor, this was semiconductor. It's not the case here. You have a metal here. You cannot have you cannot have ionized or immobile charges in a metal. Why? Because there are a huge number of electrons just near the Fermi level in the metal. They are so huge that if you just apply small potential, they are going to respond. Okay, you don't need to deplete anything in a metal. You don't need to take out electrons in a metal from the ion itself because there are already free electrons in a metal. That is the significant or main difference between a semiconductor and a metal. Okay, so there are already so many electrons present here in the near the Fermi sea that once you apply any voltage, they are ready to respond. But in semiconductor, that's not the case. You need in the semiconductor, to uh, you need to take out those particular electrons and deplete them of the electrons and leave behind the positive ions. That's why those positive ions stay here and make the depletion region. So that's what this particular difference here is, that you have a metal on this side and you have a semiconductor on this side. So you have the depletion region formed here, but on the metal side you just have electrons. You don't have negative ions. These are mobile electrons. These are immobile ions. But to balance the field, you know that it has to, whenever there is, I should say, whenever there will be positive charge here, near the positive charge, there will be negative charges attracted. Okay, so the electric field is something, oh God, electric field is, looks something like this. It just terminates at the metal. Electric field cannot exist inside the metal, from the basic electrostatics, from class 1. Okay, so that's why you don't show those electric fields inside the metal particularly, because if you have a conductor, any charge you give to the conductor that resides on its surface, the class 12th electrostatics basic, that is the property of a conductor. That conductor we used to study, that was actually a metal. Okay, and now you have this particular scenario here. That's what the scenario here is actually, and that is why in this case you have the positive ions, you have the electrons. In this case also you have the opposite band bending, but you have the depletion region here. Okay, so that is what is going to be the our topic of concern. What is going to happen when when we connect different semiconductors to the metal, and what is when we call it a rectifying contact and when we call it a ohmic contact. Now let's see that what happens is that if you have, let's say, this particular case where you have the work function of a semiconductor greater than that of a metal, you call it ohmic. Why you call it ohmic? Because you see that there is the if you have a certain some electrons present here. Oh God, what is happening? You have some electrons present here. They can just drop down into this whenever you apply any potential, because it's just it's not a hill for the electrons here anymore. But for this opposite case, if there was any electron present here, it cannot go above the barrier by its own. Or rather, if there is any electron here, it cannot go through this. It has to go above this. So that's why this acts almost like a diode. Unless and until you won't lower this particular barrier, there is no conduction going to happen. And once you let's say you have, if you apply positive and if you apply negative, you're going to lower, you apply positive on this side, you are going to lower this particular electrostatic potential energy of electrons. That means this barrier will be lowered like this, and some of the electrons will go here. You remember that uh, distribution of electrons? That is applicable every time. That is the general concept. Distribution of electrons. मेटल में भी सेम है. Although metal में बहुत मतलब Fermi function times the density of the state, it is the same concept in metals and semiconductors. Now there are so many electrons present in the Fermi C here that when you lower the barrier, the blue curve, electrons will go here. Electrons will go to the other side. Okay. On the other hand, if you apply a negative, if you apply a which colors? If you apply a negative on this side, positive on this side, this barrier will go high and it will look something like this. And now, even though these particular electrons, they cannot go above because they are below this barrier. Same concept as that of p-n junction. And conduction stops. So this acts like a p-n diode. That's why this particular acts like a rectifying contact. It has a similar concept. What if you understood p-n junction, you can understand everything, because this particular I should say the phenomena happens in every single device. The blue curve, the blue curve shows that when you apply the positive, you lower the barrier. Electrons near the Fermi C are now ready to go to the other side. Conduction takes place. The pink curve shows when you reverse bias it, when you give the opposite bias, it increases the barrier. No more electrons are able to flow. Okay, so you get a curve like this. In forward bias, you get like this. In reverse bias, you get like this. This is the rectifying. This is something called as rectifying contact. Now, in the opposite scenario, if you have a ohmic contact behaves, if you apply a positive bias, you get conduction. Negative bias, you get conduction. It doesn't matter whether there is a, it doesn't matter, or I should say the barrier doesn't stop or differentiate at all between the forward bias and the reverse bias. So that is the ideal contact we want. This is the ideal contact we want between a metal and a semiconductor. We want it to be ohmic. But unfortunately, it's very difficult to make a ohmic contact because of impurities and other things. The or because of the difference in the work function of the metal and the semiconductor. Most of the time, the semiconductor work function, if you are using N type, that is the semiconducting work function is less than that of the metal, and most of the time the Schottky barrier gets formed. Then you have different scenarios how you play with it and how you play with the barrier in order to increase the conduction of the electrons through it. Now that is this part. When you have applied, this is the forward bias case. Forward bias. Oh God. You are applying the forward bias. Remember, this is N type right here, and this is metal. You apply the forward bias, you reduce this barrier. This barrier. Okay. Now those electrons here, electron का distribution जो यहाँ पे था, they can go here. They can easily go because you have applied positive here, you have applied negative here. Positive means these electrons, these particular electrons will go on the other side, or rather it should be ulta. If you are applying if you are applying a positive here, just wait a second. I think we missed. Yes. Okay, so but the concept is going to remain the same. It doesn't matter because anyways you are going to play with this particular barrier. You apply the forward bias, this barrier looks like this. You apply the reverse bias, this barrier increases. You increase the reverse bias, this barrier increases more, and you don't have any electrons going in. But the actual thing, what we missed here, because we are applying negative here, so the electrons will go from this region to this region. That is what is the only difference. The other things are going to remain the same. Because you're applying negative on this side, that is going to supply the electrons. In other words, that's going to repel the electrons from this side, and they are going to go onto this particular side. And opposite thing is going to happen when you apply the reverse bias. And Where is the reverse bias? This is the reverse bias. This is the reverse bias. And don't get confused here with the forward and reverse bias words, because in PN junction you know that you apply a positive to P, negative to N, that you called as forward bias. But you don't have a P or an N here. So don't get confused with this. Just remember that whenever you connect a higher potential to the semiconductor here, that is the reverse bias case. And when you connect the lower potential to a semiconductor, that is the forward bias case. As simple as that. You have connected the higher potential here, lower potential here. Negative. Negative is the ground. Okay. So when you connect the positive potential here, this region goes lowers. You connected negative here, this region goes higher. Why? Negative increases the electron's potential energy. So that's why metal का side ऊपर गया and semiconductor की side lower गया. By doing that, you modulated this barrier. This barrier went like this. And now you see that there is no scenario where an electron from this side can go to this side. Only one thing can happen. What can happen? An electron can tunnel through this. Okay, this barrier, this electron can tunnel through this barrier. ये जो यहाँ पे barrier है, I'll show it like here. This is like this. Electron was here. This is the metal side. If electron has energy, it can go through the barrier, something called as thermionic emission. And that is what you might have learned in the course, that the current varies as e to the power minus q phi b divided by kt, where this is the phi b. Okay, and you have the overall equation given by Richardson equation. You might have learned that in the lectures, which is proportional to just like a diode equation, I equals to I naught e to the power qv applied by kt minus 1, where this I naught is proportional to e to the power minus q phi b by kt. This is called as Richardson's equation that actually governs this current in the Schottky diode or this particular configuration. But here, if you have an electron like this, it can go above the barrier by thermionic emission. But there is one more possibility. For electron, this particular thing is a barrier. But if you consider this electron to be a wave-like, having a wave-like nature, then this is same as that of a electron in a, I should say, a potential electron hitting a potential barrier, where this electron is a wave with wave function. When it hits this, it leaks exponentially and then appears on the other side. So this is e to the power minus alpha x, e to the power minus I kx. This is e to the power minus I kx. I should say, let's consider it spatially only. So this is plane wave, exponentially decaying wave. These are the solutions of the Schrodinger equation when an electron hits the potential barrier. Outside the potential, electron is a wave, plane wave, just like your normal waves, electromagnetic waves, monochromatic, oscillating amplitude. This is the wave function of the electron. Inside the barrier, when it hits the barrier, it exponentially decays the probability. And something weirdly, it appears on the other side of the barrier, again as a plane wave. And electrons appear on here, on this side. And this is all a quantum phenomena that happens in these Schottky diodes, basically. But you don't need to go into the deeper aspect of it, but you just need to understand what basically happens. If you consider the electron to be a wave-like particle, wave-like entity here, then you have to solve the tunneling equation, basically. Because this is like a tunneling barrier now. You have to solve the Schrodinger equation here, region 1, region 2, region 3. The Schrodinger equation gives you the probability of how many electrons can tunnel. And knowing how many electrons can tunnel to the other side, you can compute the current. Okay, if you have this barrier, you have electrons decay, appear on the other side. These are the electrons. Let's say there are 100 electrons here, and only, let's say, 4 electrons tunneled here. Then if you know number of electrons is proportional to the mod psi square of x, the probability of finding the electrons on the other side. If you know the number, you can compute the current. Okay, because current is N E V D. If you just come across this equation sometimes, this is current density, basically current per unit area. Depends upon concentration, electronic charge, drift velocity. Current basically depends upon how many number of electrons are passing through it. It's the flux. Okay, just like
Okay,
water
sir.
current. Water current is if you have a if you have region, how many water lines are passing through this particular thing, how what is the flux of the water through this particular plane, that is the water current. Similar is the how many electrons are going through this particular region, that is the electron current, and you can compute the electronic current. And but don't need to go deeper into this particular thing now. Now this is the same scenario, but you have the n-type here. You have the n-type here. That means the work function of this semiconductor is greater than that of the metal. Again, you will be having this type sort of a barrier. Okay, rather this is not a barrier at all for electrons. This is not a barrier for electrons, because when you apply negative here, positive here, electron can go here. Okay, as simple as that. Okay, all right. Now next, you have a p-type. You have a you have a work function of metal greater than that of semiconductor. Whenever you have this scenario, you have formed a Schottky barrier. This is the general rule where you get whenever you have the work function for metal greater than that of semiconductor, you have formed the Schottky barrier. Okay, now there is no scenario. Even if you apply negative here, the electron cannot go. Electron can only, if there is an electron, you apply a negative here, positive here, maybe they can go through over the barrier, or they can tunnel through it. That is the only scenario. Okay, but there is a Schottky barrier present, which needs to be taken into consideration. This is the Schottky barrier present. And now what is the next scenario? All right, so these are the all scenarios which you have. So you have n-type semiconductor, you have p-type semiconductor. What you need to only think is that what happens when phi m is greater than that of phi s, what happens when phi s is greater than phi m here, what happens when phi m is greater than phi s, what happens when phi s is greater than phi m. These are the scenarios you need to consider in the Schottky, or I should say metal semiconductor junction. I should not use the word Schottky junctions, because these are actually metal semiconductor junctions. And you need to think only in terms of rectifying, when it's rectifying contact, and when it's a ohmic contact. That's it about the metal semiconductor junctions. All right, so let's not go more deeper into it. And now we have a different scenario altogether. Now you studied about the metal semiconductor junctions. Now what is next is metal oxide semiconductor. Now the actual game begins actually. Now you have embedded oxide between it. And what happens because of that? That is totally fascinating thing which happens because of embedding this particular oxide between the metal and the semiconductor. Now you know that current cannot flow from this to this region. There is no way, because there is oxide present. Then this is an insulator. A current cannot flow through the insulator. Those electrons cannot flow through the insulator. Ideally, that's what we know. And why are we doing it? Why do we need to put a oxide between a metal and a semiconductor? It is very weird. Earlier we had a P and a N. Good. Then we said that we have a metal and N or P. That was absolutely fine. At least the current flowed. The current flowed in terms of We had rectifying behavior and we had the ohmic behavior. Here the current behaved like this, just like diode, and here the current behaved like this, Ohm's law. Now what we are doing, we have a metal, we have an oxide, we have semiconductor, N or P. So from this to this or this to this, there is no current flowing, no current, ideally. Zero current because there is oxide present. Well, then why we are doing it? That's what we are going to actually see. What is the essence of bringing in the oxide in between? Why do we want to stop the current? Why? Because we want to just modulate the carriers in the semiconductor with the help of voltage applied to the metal. We don't want the conduction to happen in certain devices, not in every device. In devices called as MOS, metal oxide semiconductors field effect transistors. This is the basic building block of a processor or anything you are using right now. So that's why we are shifting to this. Now you have a metal, you have an oxide, you have a semiconductor, and you have something called as FET. This is called as field effect transistor. What happens is that when you have this kind of a structure, if you apply, let's say, a positive bias here and a negative bias here, positive bias, let's say positive bias means there will be positive charges along this particular interface and there will be electrons along this interface. That means there will be electric field in this direction. Now what is that going to do? That is going to induce these charges here in the semiconductor just below the oxide. And where are we going to use that charge? That's what we are going to see. What are those charges going to do? That is the essence of the MOSFET or any field effect transistor. Field effect means with the help of that field which gets induced, it it makes this particular channel of electrons. This is called a channel. Okay, and now this right now is just MOS. This is just MOS. Let me duplicate it. Let me just duplicate it and show it here. Oh God, let me just show it here. This is right now, this is just MOS, what we are going to study. But in the next lecture, you will study about MOSFET. What will happen in that case? Same structure, everything, just a single difference. What is the difference? You will have a region here and a region here. This called as source, this called as drain, and करंट फ्लो होगी ऐसे और यहाँ से करंट आप मतलब जहाँ से कुछ अप्लाई होगा वोल्टेज. So this is MOSFET. That's it. That's why if you understand MOS, this particular thing, it is the building block of every field effect transistor, every transistor which is using. That's why right now directly we don't jump into source and drain contacts because they are just contacts used to extract the currents. The main thing is to induce the electrons just below the oxide. You have the metal oxide, so this is oxide, and then there is semiconductor. This is metal oxide semiconductor. You want to induce channel here. You want to make as many as electrons possible in this region because of the field applied to this metal plates. This is metal plate. Okay, so that should induce the electrons here. And whenever the electrons are induced here, what you are going to do with them? Then you are going to play. You make contacts, drain, source. यहाँ भी पोटेंशियल अप्लाई कर लो, नेगेटिव, पॉजिटिव, ग्राउंड. यहाँ भी पोटेंशियल अप्लाई कर लो, पॉजिटिव, नेगेटिव, ग्राउंड. ये विद रिस्पेक्ट टू दिस ग्राउंड है. ओके, ये सभी इसके साथ कनेक्टेड होते हैं सबस्ट्रेट के साथ. Now you are entering into a circuit business. Now what happens? This is negative, this is positive, electron gets injected because यहाँ पे electronic channel already formed है, electron यहाँ के through travel करता है, gets collected at the drain, इसीलिए इसको drain कहते हैं. Drain मतलब इसमें कुछ जा रहा है, just like our normal drains. Source मतलब यहाँ से कुछ आ रहा है, electrons. But electrons तभी यहाँ से flow कर पाएंगे जब यहाँ पे already channel induce होगी, मतलब जब यहाँ पे electron की conductivity ज़्यादा होगी. अगर यहाँ पे invert नहीं हुआ है channel, मतलब अगर यहाँ पे channel form नहीं है, so those electrons cannot move at all. Okay, when those electrons travel, they get collected here, completes the circuit, you get flow. What happens because of that flow? It is rather amazing. What happens because of that flow is, now if you apply a small voltage here, small voltage to the gate, positive. Let's say you applied a voltage of sinusoidal signal. Let's say 3 millivolt. उसकी वजह से क्या होगा, whenever you kind of feed this particular that particular voltage is going to induce the channel, and you're going to get the, you apply another set of voltage here in order to extract those currents, you're going to have a huge flow of electrons in this region. That means you have amplified this particular 3 millivolt to, let's say, 3 volt, just giving rough numbers, and that means this acts like an amplifier of current. Okay, so that is what MOSFETs are good at. Basically, any field effect transistor, or basically any transistor, is good at amplification. And one more thing it can do now is, apart from amplification, this amplification was not possible in diode. Remember this. The diode is not used as an amplifier. That's why you don't apply a small signal to diode and it gets converted to a larger signal. No. Why? Because you need a dependent source for amplifier. Now, what is that? That I don't want to go into jargons right now here, but just think about it. That in diode, if you give some signal here, you get that signal out. Simple as that. But in a MOSFET, or in a this particular structure, this is MOSFET, you can give a small signal, you get a higher signal. That's what an amplifier does. And where it's used, everywhere, in communication, in radars, in space applications, in loudspeakers, in sound systems, in all of the devices, basically everything. You increase the volume of your speakers or your earphones or whatever you guys use, you increase the volume, you are basically increasing the current to the MOSFET, and that is making the more electrons flow through it, and that is increasing the amplitude of the voltage you are giving, and that voltage is basically getting converted to a sound you are emitting. That means you have increased the volume. That's what you do. So when you have a volume knob, you have a volume knob that goes from 0 to 100. Let's say it is somewhere here. If you increase it, what you are when you are increasing it, touching your screen, you are basically increasing little bit of current sent to that particular MOSFET somewhere in your processor. That is actually increasing the electrons here in this region, and that is increasing the overall output of the particular transistor, that is amplifying the signal, and that is getting out converted, the electrical signal is getting converted to the acoustic signal with the help of speakers, and you are getting amplified output. That is what happens in all of the electronic devices. Now next time you turn a knob, just think about those electrons moving in the MOSFET. That's what actually, every time I just have this particular knob, or even rather, if you are increasing this particular brightness here, whenever I'm increasing this brightness, actually what I am doing is that I'm sending in more current to those transistors. Okay, that is amplifying the overall thing connected to the LEDs of the screen. LED को ज़्यादा करंट मिल रही है तो वो ज़्यादा लाइट इमिट करने लगता है. Okay, more photons are coming out. Similar effect. If I increase the loudspeaker, or if I increase the sorry this volume, right now I cannot increase here because it will echo. So if I increase this, What it is going to do, it is going to send more currents to those transistors which are controlling the uh, which are controlling the signals of my voice, and that gets amplified after passing through this particular transistor. And there are billions of transistors doing it. It's not a single transistor. Okay, just I think we went deeper into it, and this is quite fascinating. I don't know why people are not fascinated by electronics. Okay, so let's not discuss more about it. So now what happens? Should we cover it? What's the time? 1921. Okay, just 10 minutes. Now let me talk about this particular thing, and let me see whether it's recording or not. Okay, fine. Right. So now we have the metal semiconductor junction, not metal oxide and semiconductor. Now this is the particular scenario. You have a metal, you have a semi oxide, you have a semiconductor. This is semiconductor, this is metal. Now this is the particular scenario here. This is the equilibrium condition when there is no voltage applied. You just connected those things. Fermi level wants to be aligned, no matter what you are studying. Fermi level aligned. And in the oxide, it doesn't matter because the band gap of oxide is so huge that there are no electrons present at all in the conduction band. I mean, that's why it's insulated. It's not conducting. If this is a oxide, let me draw it here basically. If this is metal oxide semiconductor, the metal looks something like this, Fermi level, which I discussed. Oxide का जो band diagram है, that looks like this. ये जो band gap है, it is almost of the order of 9 electron volt for silicon dioxide. And then there is semiconductor, which is EC, EF, EV. Okay, so in the equilibrium scenario, all of those Fermi levels want to be aligned. Even an oxide has the, I should say, the Fermi level, but that is in the middle of the oxide. So all of those Fermi levels get aligned. Every system has a Fermi level. It doesn't matter whether it's oxide, metal, or a semiconductor. But we don't draw it inside the oxide because it doesn't matter. There are anyways no electrons in it. Free electrons. Okay, free electrons is the key word. Everything has electrons. It just depends upon what is free and what is not, what is conducting and what is not. So when we okay, this is under equilibrium, or everything remains flat. Just one thing to highlight. Does anybody know what these things are? You might have seen anywhere in the books or anything. If you guys if you guys enter for any interview in an industry or any of the placements, this is a very usually asked question. This basically means that it's not drawn to scale. Okay, don't confuse it with anything. Whenever these regions are made, it means that it's not drawn to scale. You have not exactly measured that this is 9 electron volt, this is 5 electron volt. It is just roughly drawn. Okay, so don't get confused with it whenever somebody asks you. It's a very common question asked in master's interview, in PhD interviews, wherever you apply. Okay, so this is under equilibrium. This is now you apply a positive bias. You apply a positive bias here, you apply a negative bias here. When you apply a positive bias on this side, you lower the overall electronic energy on the metallic side, and you overall increase the electronic energy on this side. And because you have applied a positive on this side, there will be positive, I should say, you have technically extracted electrons from the metallic side. Okay, they went on this particular side, and that's why those electrons are reflected here. Now you have this band bending here. Why? Because you had applied positive charge here. The negative equal opposite negative charge are going to appear on the other side, but they are not directly electrons. Why? Because you know that this is a here I have shown the p-type semiconductor, and you have negative and a hole in a p-type semiconductor. So whenever you are going to I should say fill in the take away the electrons from metal and give it to the p-type, they are going to be accepted by these holes, and the remaining things are these negatives, which are the negative ions. Okay, so those negative ions remain here. That means you have the depletion. You have depleted those ions of the free carriers, which was whole in this p-type case. This is p-type, remember. It's not n-type right here. This is p-type. Whenever the electron went from this region to this region, it went into the hole, it annihilated the holes, and remaining, what is remaining? Negative ions. These are immobile ions. Okay, so now you have negative here, you have positive charges here. Electric field is in this direction along the oxide. Inside oxide there is no charge, but through the oxide electric field has to be continuous. That is the continuity of the Maxwell's equation. Electric field has to be continuous throughout the oxide, unless and until there is no free charge present in the oxide. Remember this thing. And the electric field direction is in this side. That is what this bending is also showing. Electric field is in this direction. This is the conduction band of oxide, and electric field is also equivalent to this thing. It is applicable everywhere. Okay, it doesn't matter whether it's oxide conduction band or semiconductor conduction band. Okay, that means now यहाँ पे ये region form हो गया, depletion region. That's why this particular regime is called a depletion regime. When you apply the positive voltage to the metal side and negative voltage to the semiconductor, the bands near the oxide gets bent like this. Why it gets bent like this? Because here you have a positive charge. यहाँ पे जो इलेक्ट्रॉन होगा उसको बहुत कम एनर्जी स्पेंड करनी है वहां रहने के लिए, क्योंकि पॉजिटिव एंड नेगेटिव अट्रैक्ट करते हैं, ठीक है, तो वो वहां रहना चाहेगा, तो मतलब उसकी पोटेंशियल एनर्जी है वो कम हो गई वहां, उसको उसको एनर्जी स्पेंड बहुत कम करनी है वहां रहने के लिए इस रीजन पे इसीलिए वो बैंड बेंडिंग नीचे है, क्योंकि इलेक्ट्रॉन वहां रहना चाहेगा ऑलरेडी, क्योंकि इस साइड से पॉजिटिव चार्जेस है. ओके, बट but it cannot go through the oxide. It just stays at the oxide interface. It just stays here at this interface. It does not go through it. Now, what happens when you give more voltage, more positive voltage? Okay, now this is the scenario. When you give more positive voltage, you inject some more electrons. You give positive here, negative here, you inject so many number of electrons here, you technically push the electrons from the I should say atoms. Now you take out the electrons from those particular atoms. Now they get particularly accumulated here. Now you are bringing in more electrons here. Earlier there were fewer no electrons, there were only negative ions, depletion region. Now you are bringing in electrons that are going to stay at this particular region. Now the electrons come. Earlier there were only negative ions, because of which the band bending come. Now in the case when the voltage is much greater than zero, or voltage is much greater, the electronic concentration at this region increases now. In addition to those negative ions, and you see that there is more bending of this, because the greater the slope of this band, more is the electric field. You see here the slope is this, the slope is this. The slope increases, that means the overall electric field amplitude increases. Earlier the slope was this, now the slope is this. Electric field amplitude increased. Now you have more positive charges here. Now here you have electrons plus immobile ions because of depletion. But now you have it is the scenario that you have depleted all of the ions in it, and now only thing remaining are electrons. They are going to stay near it. Okay, so when you draw the space charge of it, let me draw the space charge of it. How you draw it? You show when V is greater than 0, you get a space charge region like this, negative ions. And in the metal, positive plus Q charge. Why I am showing delta function? Because they are going to remain near the surface. They are not going to, there is no depletion. There are no depleted charges in the metal. There are only free charges in the metal. That's why there is a delta function, delta charge just near the surface, exactly near the surface, near the interface of the metal and oxide. There is a layer of charges present that remain there. They are not, I should say, they are not depleted. They are not immobile ions. They are free charges. This was for V greater than zero. Now, if you have V much greater than zero, you have electrons here now, and those electrons form a region like this, where they are exponentially decreasing with the x. This is x, and you increase this plus q more. This is plus q because you have now v much greater than zero. So और ज्यादा पॉजिटिव चार्ज आ गया, यहाँ इलेक्ट्रॉन्स आ गए now, क्योंकि क्योंकि you have already depleted all of the you have already depleted all of the ions or all of those particular holes. Now those all extra electrons, they are going to accumulate this region. And now this is the fascinating scenario. Now you have created a electron rich region here, which is useful in where this is that particular region, ये वाला region. Now you have electron rich region here. You can apply a voltage and you can get a conduction. That is what you are going to study in MOSFET. But this is not a MOSFET, this is MOS. But you have to understand what happens in a MOS, then only you can understand what happens in MOSFET. When this region gets formed, now you have all things, all the concepts again. You know the charge density, you can compute the electric field, you can compute the potential, just like you did in p-n diode. Okay, so that is what. Let me just not discuss the accumulation here, region here. Accumulation is just the ulta. You apply negative here, you apply positive here. You will be having the band bending in opposite direction where there are holes here now. Okay, होल्स यहाँ पे प्रेजेंट आ जाते हैं एंड यहाँ पे नेगेटिव चार्जेस इलेक्ट्रॉन्स आ जाते हैं एंड द फील्ड इज इन दिस डायरेक्शन. दैट्स व्हाट दिस बेंडिंग शोज. ओके, उल्टी बेंडिंग. यहाँ पे इस डायरेक्शन में बेंडिंग था एंड यहाँ पे इस डायरेक्शन में बेंडिंग है. द स्लोप ऑफ दिस energy band always gives you the electric field. Doesn't matter whether it's oxide or semiconductor. But this is what actually happens. And I think we spent a lot of time. Maybe we can discuss it in the next lecture. So we will pause here. We will go to the problems. But this is the overall scenario that's going to help you in understanding what happens in the MOSFETs and all of the upcoming devices. And I think I have given you this particular concept here. So this is the actual scenario. V much greater than zero. These are the negative ions. These are the electrons, blue. They are exponentially decreasing from the oxide region, from the oxide interface. This is the delta function of charges plus Q charges in the metal. When you draw the electric field, notice that this is the oxide basically from up to this point. This is oxide. So up to this point, this is oxide. So electric field inside the oxide is constant. Again, same concept which I discussed in the, I think, second or third lecture. Now you have to go from charge to electric field. You have to integrate the charge. Okay. And you know this is delta function. इसको जब इंटीग्रेट करेंगे यूनिट स्टेप फंक्शन देगा. यूनिट स्टेप फंक्शन को इंटीग्रेट करेंगे रैंप फंक्शन देगा. रैंप फंक्शन को इंटीग्रेट करेंगे पैराबोलिक देगा. अब यहाँ पे डेल्टा फंक्शन था, इंटीग्रेट किया, इट विल गिव अस यूनिट स्टेप फंक्शन, a step that is basically showing the electric field is constant in the oxide, in the oxide. Inside the metal it cannot exist. And यहाँ पे यूनिट स्टेप है तो रैंप है, रैंप फंक्शन as an electric field. All right, so this is the electric field profile like this and that, and then it's here. That means at this region it drops, electric field drops at this particular region. electric field drops at this particular region. That means there's a voltage drop here, and you have to go from electric field to potential. That means potential is minus integral of E dot dx. अब इसको इंटीग्रेट करना है, तो यूनिट स्टेप को इंटीग्रेट करोगे तो रैंप मिलेगा, रैंप, and inside the metal is an equipotential surface. The potential is constant throughout. That's why the potential is constant potential. Okay, why? Electric field equals to dV by dx. इलेक्ट्रिक फील्ड जीरो था, दैट मीन्स dV by dx जीरो है मेटल में, इन मेटल, दैट मीन्स V कांस्टेंट है, V कांस्टेंट। ऑक्साइड के अंदर इलेक्ट्रिक फील्ड कांस्टेंट था, तो यहीं से पता चल जाएगा dV by dx इक्वल्स टू इलेक्ट्रिक फील्ड। अगर इलेक्ट्रिक फील्ड एक कांस्टेंट मानते हैं, लेट्स से A, तो dV by dx इक्वल्स टू A, दैट मीन्स V इक्वल्स टू AX। यहाँ पे एक्चुअली माइनस है ना, V equals to minus AX. It's a straight line with negative slope. It's a straight line with negative slope, ramp. That is what ramp is, negative with negative slope. So you got a ramp, and then यहाँ पे ramp था, उसको इंटीग्रेट किया तो पैराबोलिक आ गया, ये ब्लू कर्व। फिर से ये सेम कॉन्सेप्ट, dV by dx is equal to minus electric field. Let's say electric field कुछ एक पैराबोलिक फंक्शन है, let's say पैराबोलिक फंक्शन ऑफ व्हाट, x, नहीं, इलेक्ट्रिक फील्ड यहाँ पे लीनियर फंक्शन ऑफ x था, let's say it was some minus a times x, तो dV by dx is minus a times x, integrating both sides with respect to x, you get v as a function of x is minus ax square divided by 2 plus some c. It is parabolic, x square मगर माइनस, तो ये पैराबोलिक है। तो दिस इज द पोटेंशियल प्रोफाइल, दैट मीन्स पोटेंशियल ड्रॉप यहाँ पे हो रहा है, विच इज बेसिकली which basically happens, you have an oxide in between two conducting systems, वहां पे पोटेंशियल वोल्टेज ड्रॉप हो जाएगा बिकॉज कंडक्ट ही नहीं हो रहा है कुछ। सो दैट इज व्हाट दिस इज शोइंग, पोटेंशियल ड्रॉप यहाँ पे एंड देन इन दिस रीजन, okay, there's a potential drop, and this is the potential profile of it. Okay, so this is the overall scenario of what happens in the MOS, similar to that of PN. Same rules, same electrostatics. You don't need to consider any jargons or anything. Now, directly moving on to the questions. Okay, I hope now questions will be quite a cakewalk for you guys, because I've considered, I've discussed all of the concepts. Which of the following is defined as a work function of a metal? The work function of a metal is the energy difference between the vacuum and the Fermi energy of a metal. So this is the energy required to move an electron from Fermi level of a metal to the vacuum, what we have discussed earlier. So it's the energy required to move an electron from the Fermi level to the vacuum. That is the answer of this question. Okay, what we have discussed already. Here you have for the Schottky diode, that means a metal plus semiconductor contact, metal semiconductor junction. Consider the Schottky diode from metal made up of N-type semiconductor. So you have semiconductor which is N-type, and you have a metal here. The doping of semiconductor follows an abrupt profile. This is important. The profile is abrupt, means there is abrupt junction. The junction terminates abruptly. If it was linear, then the linear profile increases like this. The doping, abrupt junction follows like this. Abruptly it drops to zero. Okay. Now the work function of a metal is greater than semiconductor, which should be the case. The charge configuration of such a device is given by which figure? So now you have in equilibrium condition you have Schottky barrier formed, and you know that on the metallic side you cannot have something like this. You cannot have a spreaded immobile ions as a charge density. Okay, so that is absolutely wrong. You can have a delta function. You can have a free charges on the metallic side, which may reside near the interface. Okay, on the metal, and the question says that it is an abrupt junction. That means the only possibility is this particular thing. Why? Because on the semiconductor side, this is the particular abrupt junction, and on the metallic side there are negative charges. Why? Because ये ऐसे था, तो जब ये जंक्शन बना था तो इलेक्ट्रॉन यहाँ से यहाँ गया था. दैट मीन्स यहाँ पे नेगेटिव चार्जेस आ गए थे मेटल में, एंड यहाँ पे पॉजिटिव आयंस. वाई पॉजिटिव आयंस? बिकॉज ये एन टाइप था, तो ये डिप्लीशन रीजन है. दिस इज डिप्लीशन रीजन. So these are positive ions and these are negative electrons. That is the charge profile of it. As simple as that. If you know the charge profile, you can draw the electric field by integrating it. Okay, it will look something like this. And if you know it, this is electric field. If you know this, you can get a potential. Again, the same scenario which I showed in the last slide. So that is the overall concept. This particular thing would have been the case. This is something called as linear profile, linear doping profile. Note that you only dope on the semiconductor side. You don't dope a metal because metal already has huge number of electrons. You dope a semiconductor in order to increase its conductivity, okay, and reduce the resistivity, because you know that conductivity is NQ mobility. You increase the N, you increase the conductivity. Okay, from the basic something called as Drude model. Simple as that. That's why you dope it. Question
Sir, I have a
3.
question. Can I ask?
Yes, yes, you can ask.
In the Schottky diode, in the
Hmm.
depletion region, there will be electric field generated at there, right? If you apply forward bias, this electric
Hmm.
field will become zero because the depletion region will also get smaller
No, it
and
won't.
smaller.
It won't become zero. Just like in case of a diode, when you have a built-in electric field, when you have a built-in electric field in the diode, if you apply a potential, forward potential, no doubt this particular depletion width gets reduced. If you apply the VA increases in a forward bias, depletion width reduces, electric field also reduces. Okay, that means the built-in potential also reduces overall. That reduces it. It doesn't become zero. You cannot totally vanish it. That region has to remain there. Okay. Otherwise, if that region is not there, the diode will get destroyed. You got it. So that's why you
Yes.
never apply a voltage greater than built-in voltage in the diode. It's never done. You most of the times you apply zero point 0.7, zero point 0.8. Once it hits that zero point 0.7 volt, exponential increase in the current is seen. And that exponential means that that exponential is itself telling us that if you just applied a little bit of voltage now, it will shoot up. The current will shoot up so much so that the diode is going to heat up and it's going to burn. So that's why you never operate in that regime. If you want to totally make the internal built-in voltage or built-in potential or built-in electric field to be zero, you have to destroy the diode. Okay, that is the
Okay,
only
sir. So
scenario
this
which you can think.
threshold voltage and built-in potential both are same or
They are
different?
not. They are not. They are not same actually. Threshold voltage is basically a circuit related parameter, which is not related to the built-in voltage. Okay, because you never measure I should say the built-in voltage cannot be measured externally. Okay, that is the very misconception. If you have this particular built-in voltage here, which is equal to zero point 0.7 for a diode, it's not measured externally by probing it. You cannot probe it. You cannot probe it with the external device. If you have a diode, you connect a meter to a diode, it does not measure zero point 0.7, it measures zero. Why? Because the current is not flowing. The built-in voltage is internal of that particular diode, but you cannot measure it. The only thing you can measure is when you apply the particular current to it, that current flows, then the potential across it you can measure. The internal, that particular potential, you cannot measure it. Okay, just kind of remember this point always, because that's mostly a misconception among the students, and that's mostly asked in interviews. It doesn't matter whether it's an interview for a, if you are applying for any of the jobs or industries, or even for as a assistant profs to some of the universities, or any of the colleges. This is the fundamental question that's asked to people.
Okay, sir. So the
Sir,
electron
if
just
threshold,
climbs, like it won't rises. Electron won't go till it get rises and equilibrium. It will climb and go that side in presence of bias. Is it?
Yes. I mean, when we apply the bias, we actually play with this barrier. When you increase the bias, you reduce this barrier. तो इलेक्ट्रॉन के पास ऑलरेडी एनर्जी है कि वो डिफ्यूज होके दूसरे साइड से जाएगा. ठीक है. अब अगर ऐसा सिनेरियो सोचो कि इतना बायस अप्लाई कर दिया कि बैंड ही फ्लैट हो गया. ठीक है. तो दैट इज कॉल्ड रन अवे. एंड एक्सपोनेंशियल करंट इतनी इंक्रीज हो जाएगी कि डायोड विल हीट अप सो मच सो दैट इट गेट्स डिस्ट्रॉयड. यू गॉट द पॉइंट. वी जस्ट वांट टू अप्लाई दैट स्मॉल वोल्टेज की जिसकी वजह से कंडक्शन पॉसिबल हो. ओके. Now
sir,
there
if
are
threshold voltage
now
increase
there
or
are
decrease,
let me finish. Now there are diodes called as power diodes. ये पावर इलेक्ट्रॉनिक्स वाले यूज करते हैं, मतलब हाई पावर के लिए यूज होते हैं. These diodes can handle a current of the order of amperes, but the diodes we study mostly in electronics, mostly in semiconductors, they are not made to handle huge currents and huge voltages. If you want to make a diode which is going to handle huge currents and huge voltage, we have to do the modification in the diode in terms of doping, in terms of maybe add another region or something like that. Then that makes it a power diode. और ये power electronics में use होता है, made up of maybe silicon carbide or germanium, something they use. But वो बहुत ज़्यादा voltage और current handling capability होता है, क्योंकि ये मोस्टली कहाँ पे यूज होते हैं कि चार्जिंग वगैरह में पर्टिकुलरली वो यूज करते हैं. अगर कोई हाई पावर चार्जर है, 25 वॉट का चार्जर है, या मे बी लैपटॉप का चार्जर 150 वॉट्स है, तो दिस इज ह्यूज पावर एज कम्पेयर टू दैट ऑफ अगर कोई डायोड बेसिक प्रोसेसर में यूज होता है, वो कितना ही पावर कंज्यूम करता है. दैट कंज्यूम्स ऑफ द ऑर्डर ऑफ मे बी माइक्रोवाट और मिलीवाट पावर. सो उसमें उतनी ज्यादा करंट और वोल्टेज की रिक्वायरमेंट नहीं होती है. ठीक है. That's why most of the diodes we are talking about here are normal low power diodes. Yeah, you have a question. Just a little bit fast because we are lagging. Someone was having a question, I guess.
sir, threshold voltage, sir, increase or decrease, what happens, sir?
With what?
If if threshold voltage is increase or decrease,
Because of
it is
what?
a, because of what?
Hmm?
Uh,
I don't
uh,
get your question. You have a question that threshold voltage increases or decreases because of what?
yes,
Temperature.
sir. Yes, sir. Reduce, sir.
Huh,
Uh,
that was the assignment problem in previous section, previous assignment. Threshold voltage reduces because of temperature, because now electron energy has increased, and वो जो exponential Fermi tail में जो electrons है, वो इतने ज़्यादा है अब कि you have to just apply small voltage to make it conduct. You got the point?
okay, sir.
Just that is इलेक्ट्रॉन का डिस्ट्रीब्यूशन ये था एट टेम्परेचर T1, और टेम्परेचर T2 अगर इंक्रीज करोगे तो मोर इलेक्ट्रॉन्स इस रीजन में आ जाएंगे और यहाँ जाएंगे. तो अब कंडक्ट करने के लिए जो थ्रेशोल्ड वोल्टेज होगा वो कम होगा. अगर अर्लियर टेम्परेचर T1 के लिए ऐसे कंडक्ट हो रहा था, तो टेम्परेचर T2 के लिए यहाँ पे कंडक्ट होगा, ठीक है, दैट मीन्स अर्लियर कंडक्ट होगा। इसका मतलब ये जो
Okay,
थ्रेशोल्ड
sir.
वोल्टेज है, थ्रेशोल्ड वोल्टेज इज इट्स अ पैरामीटर, बिकॉज अब आपको कम वोल्टेज अप्लाई करनी है इसको कंडक्ट करवाने के लिए, बिकॉज ऑलरेडी इलेक्ट्रॉन के पास एनर्जी उतनी है कि वो डिफ्यूज होकर दूसरी साइड से जा सकता है, बिकॉज आप लोगों ने टेम्परेचर इंक्रीज किया। अब टेम्परेचर इंक्रीज मतलब केटी इंक्रीज, इलेक्ट्रॉन की काइनेटिक एनर्जी और एनर्जी इंक्रीज हो गई, और वो किस में दिखता है, वो इसमें फर्मी टेल में दिखता है, बिकॉज फर्मी फंक्शन इनटू डेंसिटी ऑफ स्टेट्स। तो इसमें केटी है फर्मी फंक्शन में, तो ये इंक्रीज हुआ तो स्प्रेड हो गया फर्मी फंक्शन, तो यू हैव टू अप्लाई लोअर वोल्टेज। Okay, let's move on fast. I
Whether
think
you
we're lagging.
said, whether you said that previously that we can give current and measure the voltage uh, for this threshold voltage. Is it the case, or will source the voltage and measure the current? Like I didn't get that point actually.
Okay, my point was that if you have a diode and you have a built-in potential here, which is built-in potential, this is zero point 0.7 and this is computed by the that kT by Q ln of depends upon the doping. You see
Yes,
that
sir.
it
Yes,
the relation itself says that it depends only on the doping. If you want to change it, you have to play with the doping, as well as you can modulate the barrier by applying the external potential. But the thing is that you don't measure it externally. If you externally, how do you measure some voltage? You apply voltmeter here, let's say multimeter apply कर दिया and यहाँ पे voltage measure
yes.
कर रहा है.
Mm.
It's not going to measure the inbuilt potential of this. You see that there is a problem. You are connecting it to the external parts of the diode right here. And क्या होता है कि यहाँ पे जो जैसे whenever you connect these particular things, यहाँ पे अलग से एक bending आ जाती है, because ये metal leads होते हैं, ठीक है,
Ah,
यहाँ पे एक ऐसी bending आ जाती है, a different
okay.
overall bending. That's why you never measure a built-in voltage of a diode when you connect it to a voltmeter. What you can do, if you have a diode, you apply voltage, a current flows inside, overall current, diode current, which is given by I naught e to the power QE by KT minus 1. Now, what you can do, that because of this particular voltage, because you have applied some voltage, let's say zero point 0.7 volt,
Yeah.
then there will
Yes.
be across this particular thing there will be zero point 0.7 volt. Obviously, there will be some drop also because of the resistance
Okay.
of this. But now you have all
Okay.
applied, then you can measure it. But because this particular thing you have not applied any voltage, a voltage is throughout it is zero because you have not applied anything. The current should not flow without applying
Oh,
anything.
okay. 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 Yeah, I got it.
Okay, by itself
Yes,
current
sir.
cannot flow, because if there is potential, that means it should work without applying anything external force. Okay, that will be
Yeah.
the
I got
violation
it.
of law of thermodynamics.
Yeah. Thank
And
you, sir.
you got it.
Yes. Yes.
Okay, fine. Let me just move on quickly. I think these questions are quite easy now, because if you have understood the previous concepts, then it becomes easy. Now the question for this is that equilibrium energy band diagram for an ideal metal semiconductor. Ideal metal semiconductor is shown. Answer the questions below. Remember that this is n-type here. You can see from the Fermi level is closer to that of the conduction band. And you can clearly see that this particular barrier will be Schottky barrier A. Why? Because the metal work function is greater than that of the semiconductor. So that will be rectifying, and I think the answer should be this particular thing, because the metallic work function is greater than that of semiconductor, and you get a barrier like this, where you have the IV characteristics in forward something like this and reverse something like this. This is the IV characteristics. That's why it's a rectifying behavior, that whenever you apply forward bias, it will conduct and conduct like a diode. If you apply a reverse bias means negative to this, positive to this. Forward bias means positive here, negative here. It is going to act like a off switch. Now, what is for the B part? For the B part, you can see that it's an ohmic contact, because what is going to happen here? It's going to conduct something like this. The IV is going to look something like this. Whenever you connect a positive here, negative here, the current is going to flow. the negative here and positive here, the current is going to flow. It's not going to matter for it. So this behavior is, I should say, the ideal contact what we want to make. But it depends definitely upon the work functions of the metal and semiconductor. So for the B part, it's going to be ohmic because the semiconducting work function is greater than, oops, not the rectifying. Semiconducting work function is greater than that of the metallic work function. Was it the case or is it ulta? That is the case. Okay, because it's n-type. This is n-type also. Yes. Okay, so hmm, इस केस में even if you apply you apply a negative charge here, the electrons move from this region to this region, and the current flows in this direction. You apply a positive charge here, electrons move in opposite direction. Okay, so you get current flow both ways. But in this particular, if you apply a negative here, that means reverse bias. The electron, there is only one way for the electron to go, that means it can tunnel. If we neglect tunneling, the electron cannot go through this barrier, which is the Schottky barrier, and it acts like off switch. Now, if you apply positive here, then this barrier reduces, and you can get the electron from this region to this region. That means it's almost like a diode. Okay, so that's what the working is. Now, copper, what is this? Copper is deposited on n-type silicon. Copper is a metal deposited on n-type silicon to form an ideal Schottky diode. Okay, the work function is given, electron affinity is given. We have to compute Schottky barrier. So it will form a barrier like this, where this is the Schottky barrier. This is the work function of metal. I should not show it like this. The Fermi level has to be same. This is the Fermi level. This is the conduction band. What is given? Electron affinity. Let's say somewhere here there is a vacuum level. What is given? This is electron affinity 4.03 electron volt, and work function of metal is given as 4.65 electron volt. We just showed that this particular barrier height can be computed from work function of metal minus the electron affinity of a semiconductor. You just have to subtract these two.
Yeah,
As simple as that.
0.62.
Exactly. This is really quite a cakewalk. You get the Schottky barrier height. If you multiply it with Q, you get in terms of electrostatic energy. But if you remove the Q, you get the potential. Maybe that might sometimes confuse you. Okay. So, what is next? Built-in potential in a copper Schottky diode is. This built-in potential is same what happens in case of a diode also. But now here you have only charges on the one side. That means you will be having built-in potential like kT by Q ln of Na divided by Ni only, or Nd rather, because it's n type here, I guess. Yeah, it was n type, Nd. So now what do you have to calculate is the built-in potential. Now this built-in potential, this is the built-in potential. This is the barrier. This is the Schottky barrier. This is the built-in potential. Okay, don't get confused with it. So this particular thing you need to compute, and how you're going to compute is because just simple, I should say from the figure itself. ये लेवल को अगर यहाँ पे कंसिडर करोगे कंडक्शन बैंड को ऐसे, और ये ब्लू में फर्मी लेवल है, एंड ये जो ब्लैक में है ये बिल्ट इन पोटेंशियल है यहाँ से यहाँ तक, और ये भी ये यहाँ तक शॉर्टकी बैरियर है. तो टेक्निकली निकालना क्या है, बिल्ट इन पोटेंशियल निकालना है. तो हमें क्या क्या चाहिए, हमें ये पता है और हमें ये भी पता है, ई सी ई एफ की डिफरेंस, ई सी माइनस ई एफ, ये हम निकाल सकते हैं अगर डोपिंग दी होगी। तो टेक्निकली ये जो बिल्ट इन पोटेंशियल होगा ये बराबर होगा शॉट की बैरियर हाइट, ये हाइट माइनस ये हाइट, दैट्स इट, माइनस ई सी माइनस ई एफ, सिंपल एज दैट. So that's going to give you the built-in potential overall this thing. मतलब we subtracted from this thing, we subtracted this thing. It's going to give you this thing. That's it. That's the built-in potential. Now just we have to put the values. Phi b, I think it's given as 0.62, or we found it in the last question. Now we found it in the last question, 0.62, and how are we going to compute the EC minus EF? You can compute it directly using the equations of the diode, or you can compute it by this particular thing. This is EG overall, and let's say you have a intrinsic level, something like this. Then you can compute the what is that? EC minus EF will be basically equivalent to EG by 2 minus KT by Q ln of ND over Ni. Same thing what happens in the diode. This is just from the diode. Okay, so this particular thing is EG by 2. Okay, and and what else? Yes, so you just have to be careful with that. Now you put the values inside, you get VBI is equivalent to phi B, what was it? Minus EG by 2 minus KT by Q ln of ND by Ni. Everything is, I guess, given. Phi b is given, EG you know, this particular thing you know, ND is given, Ni is given. Just put the values. I guess you get VBI to be approximately 0.45. Oops. Why have we got 0.45? Oh, it's 0.43. Okay,
0.4.
0.43. Okay, so that's the answer of this question. But the main concept is you need to consider the energy levels what you are given, and you should be fast enough to think how you are going to compute any energy level and what you are given in the system. Okay, let's move on to the other
Yes,
question.
sir.
You have any question? Okay,
No, sir.
for the for measuring the depletion width again, now what you are going to do, use the same thing. What you have the depletion width for the, the for case of PN diode, you got the depletion width as something like this. Let's remove this because we're not applying anything, and we don't have this region here. We don't have Na, so you get 2 epsilon by Q 1 by Nd times the V built in. This is the simple for this metal semiconductor junction. Exactly same. Okay, so I think everything is now here given. You know the built-in voltage, you know the ND, you're going to compute the depletion width in the micrometers. You're going to get the answer as 2.73. Everything is given. The
Sir,
doping is given.
sir, epsilon, sir.
Epsilon is epsilon for the silicon. Epsilon for there was the silicon. Yeah, epsilon for the silicon. You have to take as epsilon naught, epsilon r. This is 8.85 into 10 to the power minus 12 farad per meter, and this is, I guess, I think it's 12, 11.9.
Okay, sir.
Done. Okay.
Okay,
Yeah,
sir.
yeah. This it is given here. Epsilon s is given here. Okay. Everything would be given. This is just a formula-based problem. Just have to understand the main concepts. And now moving on to the final part, which was the MOS, which we discussed lastly. What happens is that simplified. These are the simplified MOS diagrams. Match the energy band diagram with the labels. First of all, this is p-type here because Fermi level is close to the valence band. This is n-type. This is n-type. All right. Now the problem becomes simpler because you know at least one part, that this is p-type, this is
Answer
n-type.
three will be three, sir.
Yeah, it'll be three. Just let me explain. Just don't directly jump onto the question answers. So, so what is going to happen is that they have connected the metal, oxide, and semiconductor, and the bands are going to how the bands are going to bend. Again, it depends upon the work function of the metal and the work function of the semiconductor, the Fermi level of the metal and the Fermi level of the semiconductor, Fermi level of semiconductor. Now, in this particular case, uh, when the electrons, when the contact is made between the metal oxide and the semiconductor, electrons will, I should say, this particular level is going to go down, and there will be equilibrium. There will be single Fermi level in the equilibrium, and as such, the bands will bend in this particular fashion. Okay, this oxide has been shown not to scale. There will be bending in the oxide also. Okay, just like this bending, what I showed actually. But this is not drawn to scale. This is just shown as a bend. This is just shown as a flat, but that's not going to happen. So, what do you call, whether you call this as PMOS or NMOS, it depends upon what type of charges you have. Okay, so in the I think the answer for this is fourth one. This one. It's not the third, because whenever you have the p type here, you have more electrons here. That means it's NMOS. N means electrons are the uh, carriers, charge carriers. Okay, current is going to flow because of that. I mean, when you make a MOSFET, in the MOS, when the carriers below the oxide are electrons, that you call it NMOS, where N is the electrons, and in the N type you have the holes here. You call it PMOS. P means because of holes. The carriers are the holes. Again, you have the N type here. You have the holes here. Okay, this is the accumulation region. Accumulation of holes. Okay, and the this particular case, the voltage has been applied, and that's why there is accumulation of the holes in this particular region. Otherwise, under equilibrium conditions, the bands should be flat. Okay, the band should be flat, ideally. If this is N-type, ideally under equilibrium, it looks something like this. This is the conduction band, this is the Fermi level of metal. Let's not confuse you by drawing the Fermi level inside oxide, but there will be Fermi level somewhere in the middle of it. This is valence band, and this is equilibrium condition. But the bending here shows that there is some non-equilibrium condition. But there can be actually bending even in equilibrium when you study something about non-ideality. If there are charges in the oxide, or if there are traps present, if there are maybe ions present in the oxide, it can give rise to non-ideal conditions which can create band bending. But whatever you have studied till now, you know that at equilibrium the bands will be flat no matter what you are studying, whether it's PN, whether it's BJT, whether it's I should say the MOS, whether it's MOSFET. A flat means the Fermi level is going to be fully aligned in the entire region. Okay, and the answer of this question is C, because P represents the holes are the carriers of the holes are getting accumulated near the oxide and semiconducting interface. They are the carriers there, and N means the electrons would be the carriers there. That's simple as that. Now, what is going to be the other question? Identify the sign of applied voltage. Yes, the voltage is applied in the previous questions. That's what I was telling. So, what is going to happen in this particular scene? You see that there is accumulation of the holes. So 2 and 3, there is accumulation, or rather, is there any misconception here in the question. This is n-type, there will be holes. Okay, yeah, there is accumulation of holes, but the overall regime is it is inverted. Yes, exactly. Inverted means the majority carrier here were the electrons, but because of applying potential, you have inverted this region. Inverted means उल्टा कर दिया. तो अब यहाँ पे होल्स आ गए बिकॉज ऑफ इन्वर्जन. ये एक्यूमुलेशन मैंने वर्ड इसलिए यूज किया क्योंकि एक्यूमुलेट हो गए यहाँ पे होल्स, लेकिन इट्स नॉट द रिजीम एक्यूमुलेशन रिजीम. ओके, डोंट गेट कंफ्यूज्ड विद इट. व्हाट आई मीन टू से,
Can you explain what is inverted again? Like, I didn't get.
I'll try to simplify it for you. What I mean to say is that let's not confuse you with it. What I mean to say is that when you applied the I'm considering this condition. When you applied the voltage here, you bended the bands like this. Okay, so you see that there, this is the intrinsic level, this is the Fermi level, this is the Fermi level. Oh God. This is the conduction band, this is the valence band, this is the intrinsic level. So ये n type था, और यहाँ से जो metal है, metal पे you have, oh, where is that, yes. तो ये bending कब आ जाएगी इस side से, when you, let's say they have not drawn the oxide, but oxide will bend something like this also, जो कि यहाँ पे नहीं दिखाया है इन्होंने, which they should show because they'll be bending in the oxide also. Okay, so the electric field is in this direction. That means you have a positive here, negative here. That means ये यहाँ जाएगा, ये फर्मी लेवल है मेटल की, और ये इसकी फर्मी लेवल है, मतलब ये हाई नॉन इक्विलिब्रियम कंडीशन है. मतलब यहाँ पे नेगेटिव अप्लाई किया है, यहाँ पे पॉजिटिव अप्लाई किया है, तब जाके ये ऐसी बेंडिंग होगी. ठीक है. Why and how I know that this type of bending will occur? Because you have to start from the basics every time. You have n-type, and you have metal. You join it and you have oxide between. Don't forget the oxide. Otherwise it will form a short key. When you connect it, everything will be flat under equilibrium. Just connecting it. Done. Apply the voltage. How you apply the voltage? Connect, पहले connect positive यहाँ, negative यहाँ. When you connect the negative on this side, you're going to supply the electrons. Or in other words, you're going to take the electrons from the metal and deposit into here. Okay. And because यहाँ पे already इस region में positive ions और electrons है. Positive ions और electrons है. Okay. So what is going to happen? There will be positive charges here for the near the metal oxide interface, and if you have applied, let's say, voltage greater than zero, slightly greater than zero, you make a channel like this. Let's say, because you have applied positive here, you are going to lower this particular region. You have applied negative here, you are going to increase this region. Electrostatic potential energy of the electron on this side is going to increase. Okay, so now the Fermi level here gets lowered. ये ऑक्साइड है, let's consider ऑक्साइड अभी वहीं पे, तो यहाँ से इंक्रीज हो गई फर्मी लेवल ऐसे. ठीक है. एंड इन द बल्क में सब कुछ सेम रहेगा, बस जो प्रॉब्लम है वो जो फिनोमेना है दैट हैपेंस नियर द इंटरफेस. ओके, इन द बल्क इट इज गोइंग टू रिमेन एज such what it was, n type, but those electrons whatever you give are going to go something like this. They'll be bending. Why they'll be bending? Because इलेक्ट्रॉन विल लाइक टू स्टे हियर बिकॉज यहाँ पे पॉजिटिव चार्जेस है अब। सो इलेक्ट्रॉन की पोटेंशियल एनर्जी इस रीजन में रिड्यूस हो गई बिकॉज वो पॉजिटिव चार्ज के पास रहना पसंद करेगा, सो उसको वहां पे रहने के लिए कम एनर्जी स्पेंड करनी है। दैट्स व्हाट द बेंडिंग इज एक्चुअली शोइंग। ओके, सो now what is going to happen is that if you now if you now apply the opposite voltage, now you apply the negative voltage here, positive voltage here, the bands are going to bend like this, ulta. Okay, this is the oxide, and the bending will be, this is the bending of oxide, this time bending will be like this, and now you have the ulta bending. So that is what actually happens in case of MOS under application of the bias. And here you have the holes. That means इस region में you have inverted it. Inverted means what is meant by inverted? Inverted means whatever it was before उसका उल्टा कर दिया है. You have made the opposite of it. Earlier it was n type. इसमें बहुत सारे electrons थे. Now you have made this region as like the p type. You have inverted it completely because you have increased the number of holes here. And now when it is inverted, there are more number of holes present at this particular region. It is called as inversion. You have
Okay, but
inverted
the
the channel.
material is n type.
Sorry?
But the material is n type.
Throughout
Uh,
in the bulk, yeah, material is n-type, but just near the
and
oxide and
there in that
semiconductor
region it
interface,
goes inverted.
it goes inverted. Okay,
Yes.
that's why it's
Oh,
called as
thanks.
inversion region. That is
Okay,
the
okay.
Sir, holes
uh,
में holes means positive charge, sir.
they are. I told you a couple of times that there are immobile charges, there are mobile charges. This is immobile when I show this. Ions, these are ions. This you mostly see in depletion region. Depletion depletion regime of MOS capacitor, and depletion region
So
जो
sir,
पीएन
its
जंक्शन में
effective mass
उसमें भी
will
वही
be
होता है.
higher. Ions. Like
Ions
effective mass
I
is greater than electrons.
no, that is for the holes, not for the ions. Ion is already heavier than that of the electrons as well as the holes. Ion is like the atom जिससे तुमने इलेक्ट्रॉन या होल निकाल दिया है. ओके,
Okay.
आयन विड भी, अगर मेरे पास ये एटम है ना, सिंपल क्लासिकल पिक्चर, अगर यहाँ पे दो इलेक्ट्रॉन्स है, यहाँ पे एक इलेक्ट्रॉन है, अगर कुछ प्रोसेस की वजह से यहाँ पे मैंने लाइट इस पे अप्लाई कर दी और ये जो इलेक्ट्रॉन है ये निकल गया, तो यहाँ पे एक होल आ गया. ठीक है, तो ये जो ओवरऑल पिक्चर अब है, ये ओवरऑल पिक्चर ये मैं दिखा सकता हूँ पॉजिटिव और एक होल करके. ये पॉजिटिव जो है ना, ये सारा
So
इंक्लूड करता है. गॉट इट. बट ये जो है,
Okay, sir,
ये जो
got
है,
it.
ये वाला चीज ये मोबाइल नहीं होता है. अंडर मतलब जो जो जिस रीजन में हम पढ़ते हैं ना, उस उस वोल्टेज रेंज में इसको हम टेक्निकली मूव नहीं कर सकते. ये इमोबाइल होते हैं, ये लैटिस साइट्स होते हैं. जो लैटिस साइट्स हमने क्रॉनिक पेनी में नहीं पढ़े थे ऐसे, पॉजिटिव पॉजिटिव पॉजिटिव, ये लैटिस एटम्स होते हैं. यू कैन नॉट मूव देम. यू कैन ओनली टेक इलेक्ट्रॉन्स और होल्स आउट फ्रॉम इट, बट यू कैन नॉट मूव द लैटिस एटम्स इटसेल्फ. ठीक है, मे बी बहुत ज्यादा कोई फोर्स अप्लाई करोगे तो मूव होंगे, बट जो हम चीजें पढ़ रहे होते हैं उसमें हम इनको स्टैटिक कंसिडर करते हैं, इमोबाइल. ये आयंस होते हैं, ये जो मैं यहां दिखा रहा हूं, ये वही इमोबाइल आयंस है. दीज आर नॉट मूविंग, दे डोंट टेक पार्ट इन कंडक्शन, दे जस्ट स्टे देयर, बट दे डोंट मूव एट ऑल, दे डोंट टेक पार्ट इन कंडक्शन. ये होल्स है एंड इलेक्ट्रॉन्स है, दीज आर मोबाइल, ओनली दे कैन मूव एंड टेक पार्ट इन कंडक्शन. ठीक है, तो वेन एवर let's say a depletion region gets formed, let's say ये जो थर्ड वाला ये जो सेकंड वाला था वो इन्वर्ट हो गया, तो वो दिखा दिया मैंने कि इन्वर्जन हो गया. मतलब जो पहले वहां टाइप ऑफ मटेरियल था एन टाइप, अब वो ऑक्साइड और सेमीकंडक्टर के पास पी टाइप बन गया जैसे, क्योंकि वहां होल्स आ गए, तो वो इन्वर्ट ही हो गया, तो उसको इन्वर्जन कहते हैं. अब तीसरे केस में क्या हो रहा है कि तीसरा केस इज, हाँ तीसरा केस इज दिस वन. तो तीसरे केस में क्या हो रहा है कि यहाँ पे जो चैनल है वो डिप्लीट हो गई है. डिप्लीट मतलब है कि वहां पे डिप्लीशन रीजन फॉर्म हुआ होना स्टार्ट हुआ है, बट वहां पे इमोबाइल आयंस है, ना कि मोबाइल आयंस। देखो, ये एक्चुअली इंपॉर्टेंट क्वेश्चन इसलिए है क्योंकि यहां ध्यान से देखना इसमें क्या एक्चुअल चीज है। लेट मी जस्ट रब दिस। ये जो, इफ यू सी दिस orange curve, this is the Fermi level of semiconductor, and this is the intrinsic level of semiconductor. You see that Fermi level and intrinsic level are crossing each other. Fermi level is getting lower than that of intrinsic level at this region. See this point. Fermi level intrinsic level से नीचे जा रही है, मतलब क्या है कि इस वाले रीजन में फर्मी लेवल इंट्रिंसिक लेवल से हायर है, मतलब ये एन टाइप है। बट इस वाले रीजन में फर्मी लेवल इंट्रिंसिक लेवल से लोअर है, दैट मीन्स ये पी टाइप बन गया। इसीलिए ये जो है ये एक्चुअली इन्वर्जन हो गया इसका। ठीक है, तो ये साइन है, मतलब दिस इज द साइन ऑफ स्ट्रॉन्ग इन्वर्जन, दैट यू हैव टोटली inverted the region near the oxide and semiconductor. Now, now think about this particular picture. You see that here the Fermi level touches the intrinsic level, but it does not go below the intrinsic level. That means it stays n-type throughout. But what comes here is depleted charges, depleted charges, immobile charges, depleted. Depleted of what? Depleted of electrons. क्योंकि एन टाइप था, तो एन टाइप में पॉजिटिव होते हैं और इलेक्ट्रॉन्स होते हैं। ठीक है, तो यू हैव टेकन दीज इलेक्ट्रॉन्स आउट। जब इलेक्ट्रॉन गया तो वहां पे क्या रहा, बस पॉजिटिव। और पॉजिटिव कहां पे अक्यूमुलेट, पॉजिटिव कहां पे आ जाते हैं, वो नियर द ऑक्साइड रह जाते हैं। तो ये वाला रीजन है, इसको डिप्लीशन रीजन कहते हैं इसमें। सेम जो कि पीएन जंक्शन में डिप्लीशन रीजन बनता है, because you have depleted those ions. English, this is an English word. Depleted means you have in short, you have taken something out of it, that it has now reduced from its original form. It has been depleted. It has been, I should say, इससे कुछ लिया गया है, और ये जो वहां पे अब रहा वो उसके पास कुछ कमी है। किस चीज की कमी है? इलेक्ट्रॉन्स की कमी है। ठीक है, क्योंकि इससे आप लोगों ने इलेक्ट्रॉन्स ले लिए, अब ये पॉजिटिव आयंस खाली बचे। एंड दिस पर्टिकुलर फर्मी लेवल and its position with respect to intrinsic level is important. That's why यहाँ पे depleted region है, लेकिन यहाँ वाले में inversion हुआ क्योंकि यहाँ holes थे, और ये holes mobile है। That means ये p type बन गया इस region में, green वाले region में। लेकिन ये throughout n type ही है ये वाला region, बस यहाँ पे depletion charge आ गया। और अगर इसी वाले केस में अगर आप और ज्यादा वोल्टेज अप्लाई करोगे तो ये कन्वर्ट होगा इस वाले रीजन में। ठीक है, दैट मीन्स अगर वोल्टेज इंक्रीज करोगे तो उसके बाद जो इफेक्ट है वो आना स्टार्ट हो जाएंगे। इसीलिए ये जो ये वाला रीजन है, दिस इज डिप्लीशन रीजन थर्ड वाला, एंड दिस इज इन्वर्जन रीजन। एंड ये पॉजिटिव पे डिप्लीशन इसलिए दे रहा है क्योंकि ये वाला साइड जो था ये पी टाइप है, इसमें ये एन टाइप है, ये वाला साइड। वॉट एवर हैपन्स इन द एन टाइप, opposite happens for the p type. That's why whenever you study, you only show n type devices or p type devices. You don't show both because people get confused most of the times. If you understand one type of semiconductor, metal oxide semiconductor or metal semiconductor, you have to apply the opposite rules in case of another type of semiconductor, p type. If you study n type, apply opposite to that, to the p type. So that's why these particular regions are important. Now that means what is going to happen is that uh, in this particular case, remember that Don't get confused that these are not holes, these are immobile ions, just like in a p-n junction, which are depleted of something, depleted of what? Electrons. But ये यहाँ पे p टाइप नहीं बन जाता है रीजन, क्योंकि फर्मी लेवल स्टिल इंट्रिंसिक लेवल से ऊपर है। फर्मी लेवल स्टिल इंट्रिंसिक लेवल से ऊपर है यहाँ पे। लेकिन यहाँ अगर देखोगे फर्मी लेवल इंट्रिंसिक लेवल से भी नीचे गया है, मतलब फर्मी लेवल यहाँ क्लोज है वैलेंस बैंड को, देन कंडक्शन बैंड। ठीक है, यहाँ पे कंडक्शन बैंड टू फर्मी लेवल डिस्टेंस इतनी है, और फर्मी लेवल टू वैलेंस बैंड डिस्टेंस इतनी है। दैट मीन्स ये पी लेवल, पी टाइप बन गया है यहाँ पे। पी टाइप कब बनेगा ये? जब यहाँ पे होल्स की कॉन्सेंट्रेशन ज्यादा इंक्रीज हो जाएगी। ठीक है,
Sir,
होप यू गॉट
what's
दिस
the
पॉइंट।
difference between hole and ion? Like, hole is
I
actually in the ion.
Whole is a picture which we have developed to understand the motion of the particles. Otherwise, it is just a vacant site. जैसे मैंने यहाँ पे दिखाया ना, कि मैंने दिखाया कि यहाँ पे ये इलेक्ट्रॉन था, अगर ये इलेक्ट्रॉन निकल गया तो यहाँ पे क्या रहा? होल। टेक्निकली वेकेंट साइट रह गई, वेकेंट ऑर्बिटल। ठीक है,
Yeah,
तो
that
जैसे
hole is came due to the charge of
look
the
look
nucleus.
look, you remember this thing, ek,
Yes, yes, yeah,
E versus k. This is conduction band, this is valence band. You see that इस जो बैंड है, ये बैंड में इलेक्ट्रॉन्स होते हैं full,
yeah,
these are all occupied by the electrons. What happens इनमें से, let's say if one of the electron goes to conduction band, let's say this this electron I remove, this went to the conduction band. Here, what remains? Whole
a hole.
vacant state. अब इस वेकेंट स्टेट की वजह से क्या होगा, और इसको हम एज अ पार्टिकल क्यों ट्रीट करते हैं? आई विल टेल यू इन अ लेमैन सेंस, इन अ बेसिक लैंग्वेज। इसका कुछ ओरिजिन बहुत डीप है, लेकिन आई मेक यू अंडरस्टैंड द बेसिक लैंग्वेज व्हाई इट्स ट्रीटेड एज अ पार्टिकल। once the oh god, okay, let me just charge it for 3-4 seconds. But once the electron left this particular position and went to the higher state, it left a vacant region here, which is this. अब इसकी वजह से क्या होगा, क्योंकि हमने इलेक्ट्रिक फील्ड अप्लाई किया है इस डायरेक्शन में, लेट्स से इलेक्ट्रॉन इलेक्ट्रिक फील्ड के ऑपोजिट जाना पसंद करेगा, तो ये जो इलेक्ट्रॉन है अब ये इस वेकेंट स्पेस में आ जाता है। अब यहां पे इलेक्ट्रॉन फील्ड आ जाता है, और यहां पे एक होल आ जाता है। इसी तरीके से अब ये इलेक्ट्रॉन यहां आना पसंद करेगा, तो ये अब यहां पे इलेक्ट्रॉन यहां आ गया और यहां होल रह गया। देख रहे हो क्या हो रहा है? तो ये जो ये ऊपर इलेक्ट्रॉन गया था, ये इस डायरेक्शन में जा रहा है, और ये जो ये होल था, ये होल पहले यहां था, ये लेकिन इस डायरेक्शन में अब जा रहा है। मतलब ये इलेक्ट्रॉन के ऑपोजिट बिहेव कर रहा है, इसीलिए इसको एज अ पार्टिकल ट्रीट कर रहे हैं, और एज अ ट्रीट कर रहे हैं कि होल भी जैसे मूव कर रहा है, लेकिन एक्चुअल में इलेक्ट्रॉन्स ही मूव कर रहे हैं दो डिफरेंट एनर्जी लेवल्स में। यू गॉट द पॉइंट?
Okay.
You got it, or you're confused?
Yes, sir. This is kind of exciton.
Uh, don't consider it as exciton. Exciton is a different quantity, but this is I am considering these as separate two particles. Exciton is a different thing. I'm considering just like
Okay.
electron here. There's a chain of electrons. If the if this electron went here, there is a hole here. Now this electron will come here, hole will propagate here. Now this will be electron. This electron will come here, this will be electron, this will be hole. It is just like a hole is moving in this direction. But actually it is electron moving in this direction. You got the thing? So
Okay.
that is the
Yes.
actual picture of electrons and holes. Classically. It's a classical picture. क्वांटम मैकेनिकली क्या है वो पढ़ने के लिए मुझे लगता है 3-4 साल पढ़ना पड़ेगा वो। ठीक है, ये क्लासिकली ऐसा पिक्चर हम लोगों ने बनाया है। That's why we consider it as a particle. And another reason is that now you will question, why do not we consider holes in a metal? We draw the Fermi level of a metal, we considered only electrons. We never considered
Yes.
holes.
Yes. Yeah.
We never talk about holes in a metal, but actually there are holes in a metal. There are holes in a metal. Okay. So now, when do we consider holes in a metal? That's a separate question. Now that starts to become, I should say, that's not for you to understand, but there are holes in a metal. Whenever let's say, this is Fermi level, and let's say the electrons are here, and you excite the electrons somewhat much, little bit greater than not greater than that of Fermi level, little bit, slightly greater. Electron goes here. What it leaves behind is a hole actually, and a hole can exist in a metal even. But you don't mostly talk about holes because most of the electrons are present near the Fermi level itself. अगर if this would have been a scene in semiconductors, कि most of the electrons or the Fermi level is in the conduction band, then there was no need of the whole picture in the semiconductor also. अगर semiconductor कोई ऐसा है जिसमें कि ये conduction band है, ये valence band है, और अगर Fermi level यहाँ पे है, that means यहाँ तक जो पूरे states है वो filled है, तो इलेक्ट्रॉन ऑलरेडी यहाँ पे है, तो यहाँ पे होल के पिक्चर की बात करने की जरूरत ही नहीं पड़ती. You would have just considered electrons, that's it. But because Fermi level in metal is semiconductors is here, you need to consider two different distributions. And maybe after that it will confuse you. I think we are done with this. We have just passed the threshold of our session, and my charge is also getting particularly, my pencil is totally getting depleted.
So many thanks for your details explanations, sir. Many thanks.
That's just my responsibility. Thank you. I just want to charge this. If you guys have any question, you can stay, or otherwise I'll end this session. You just charge this thing.
Sir,
Okay, thank
Yes,
lastly,
you.
sir.
previously
Yeah,
you
yeah,
were
yeah.
explained about the exciton in previous class. Can you
Mm-hmm.
just again once remind me? I actually little bit forgot and confused. Like how it won't recombine and become stable.
Uh, Luke, uh, are you a bachelor student?
No, sir, I'm first year PhD student.
Okay, that's nice. Where are you studying currently?
I sir Tirunanthapuram.
Okay, nice.
I
Okay,
am
great.
working on actually molecular electronics. Like I will
Oh, organic
sandwich
electronics.
molecules. Yes, sir. But I will study on charge transport phenomena,
All
like
right.
tunneling in proteins.
Okay, okay, nice. So, uh, what I said before was exciton is not what you consider always in a, let's say you have a electron and you have a hole. You don't always call these excitons. Why? Because most of the time this energy difference is huge. Okay, let's say you have a conduction band, you have a valence band. Let's say some trap is here. And if an electron goes from this
Sir,
to
your
conduction,
screen I think not visible.
oh shoot, okay. So when did this happen? It was visible earlier?
Just when I told question from then on, it was
Oh,
like
really?
you're speaking that by that I can understand, but
Oh,
from
just
now I
okay. Okay, okay, just let me. Okay, stop sharing. Someone's not responding. Let me rejoin. Oh, it's not showing. My Wi-Fi is stopped working somehow. Just give me a moment.
Yes, sir.
I don't know, some of my Wi-Fi signal is gone and I'm not able to connect my iPad to it, but my laptop is connected to Ethernet, so it's working on the laptop, but I don't know what is happening. Just let me still try. Okay, what is happening? What's Ethernet connection? Hello, Hemant. Hello, are you there? Okay, I guess he's not there, but what I can tell you is that maybe we can discuss it in the next session because I'm not able to. Oh God, I'm not able to connect it to my Wi-Fi right now. Again, it has completely disconnected me. I don't know whether it's a problem with Meet, but I think it's a problem with my Wi-Fi router right now. So we can discuss it next time. I'll make sure that I'll discuss about the excitons and exciton efficiency as well as the exciton transport. If you are interested in that, then I can discuss more about it. Is that okay?
Okay, sir. Interested, sir.
Okay, sure, fine. Then we can discuss it in the next section. I'll just end this session because my device is right now behaving weirdly. Maybe because it's been almost 2.5 hours we have been discussing stuff. So, okay. Okay, so let me end this session. Thank you, guys.
Thank you, sir.
Thank you. Okay, so let's start the recording.